Hello, and welcome to Fundamentals of R Programming. My name is Radia Johnson, and I will be your lecturer for this course series on bioinformatics with R. So let me tell you a little bit more about myself. Well, I'm a research scientist and bioinformatician who specializes in immunology and cancer biology. I did my PhD at the University of Toronto in immunology, and then pursued my research interests as a postdoctoral fellow and also research associate at the University of Cambridge in the UK and later at the University of Montreal. Currently, I'm based in Montreal as a research associate bioinformatician for the Rosalind and Morris Goodman Cancer Research Center at McGill University. I routinely use R and other programming languages to explore genomic data of cancer cells to identify molecular changes and risk factors that contribute to cancer development. For more information, you can consult my website, Let's Talk About Science with R, at rjbioinformatics.com, or email me directly at info@rjbioinformatics.com. You will also be able to find some of the course material on my website or on GitHub. Now let me present to you the course overview for Fundamentals of R Programming. So now let me present the overview of the course. Well, with the course Fundamentals of R Programming, we'll be learning a variety of tools and techniques and also how to write code to effectively evaluate our data structures. These videos will allow you to gain useful experience and knowledge working with R data structures, manipulating data sets in R, visualizing this data as plots or other images, basic R tools or other packages. We will also learn how to use control statements and useful debugging tools to help you when you're writing your own code. Later, we will learn the basics of evaluating probability distributions, get hypothesis testing, and statistical modeling with R. The aims of this course are to provide you with a sufficient overview of built-in functions and packages available in R for scientific computing, more specifically to meet your bioinformatic needs. This course focuses on R data structures and visualization methods available in R to explore data. We will review various statistical methods available in R for hypothesis testing and fitting probability distributions. This course will allow you to also explore the basics of statistical modeling and methods used to explore linear models. So these are all useful tools for scientific computing, but also for people who do or would like to learn more on bioinformatics, and also great for people who want to learn more on bioinformatics. So the prerequisites for this course are to install the R package, which is necessary for the exercises, which you will see in the code for each exercise provided on GitHub or on my website. You will need to install the latest version of R, or at least version 3.30, where all the code has been tested and run. If you are having difficulties installing the packages, you can consult the CRAN web page or Bioconductor pages that are relevant to the packages that you need to install. Essentially, you just need to use the install.packages, your package in quotation marks, or you need to use source the BioCLite code and then use the BioCLite function with the package name again in quotation marks. Prior knowledge of statistical and bioinformatics is beneficial but not necessary to take this course, and our target audience is really for beginners or even intermediate R users, bioinformaticians, and our target audience is for beginners or even intermediate R users, bioinformaticians, and biostatisticians who are interested in using R for their programming needs or scientific computing needs. Let's begin the journey together, and I hope to see you in the next video. Hi, and welcome to the Fundamentals of R Programming. In this section, we are going to learn about R data structures. Specifically, we are going to take a look at how to create and work with vectors, lists, attributes, multidimensional arrays, matrices, data frames, and factors, and how to load and save data objects in R. Now let's move on to the first video of this section entitled Working with Vectors. In this video, you will learn how to create and retrieve information stored in vectors. More specifically, in this video we're going to take a look at how to create and work with different classes of vectors and perform basic arithmetic and set-based operations, and to learn different techniques to search and retrieve information stored in vectors. Let's begin by creating a vector. To do so, we will use the C function, which combines the numbers or strings separated by commas into a vector. For example, we will store the numbers 1, 2, and 3 into a vector object called x. You can create this vector also by saying x equals C 1, 2, and 3. 1, 2, and 3 separated by commas, of course. Now let's take a look at how to create different types of vectors. First, by copying and pasting the code here for integer vectors, you see that to create an integer vector, each value is followed by the letter L. That specifies that these are integers and not just floating point numbers or numeric values. Then we can create a logical vector using T for true or writing out the word true, and F for false or writing out the word false. Then we can create a character vector with the words apple, pear, red, green, and these are my favorite fruits and colors, as follows. Also, we can create a numeric vector, or also known in R as a double vector, again, this time using floating point numbers 1, 3.4, 5, and 10. So if we copy and paste, let's visualize the contents of the code that let's visualize the contents of the vectors we've just created by copying and pasting them into R. And behold, it prints the values that we've stored in them. We can check the class of the vectors that we've created by using the class function. So for example, let's do class integer vector, where you see it returns integer, and class numeric vector, where it returns numeric. You can also mix different types of vectors. For example, we can create a mixed vector that combines the character vector with the numeric vector. So now we've created a mixed vector, and as you can see, when we check the class with the class function, it shows us that the characters, you can see that it has coerced our numeric values into strings. This is because vectors can only be of one type. So if you mix numbers and strings, your vector will be coerced into the most flexible type. The most to the least flexible vector types in R are character, numeric, integer, and logical. So this means that if you mix numeric values with strings, your vector will be coerced into a character vector because this is the most flexible type of the two. Next, a great way to inspect objects is to use the str function, which essentially looks at the structure of the object. This allows you to see the first elements of and the length of the object together with the type of vector. So as you can see, character vector, you have CHR, it shows us that there are 5 elements, the int for integer, and logi for logical vector. Another useful tool is the length function, because this will tell us the number of elements that are present in the vector. For example, we can take a look at the length of the integer vector, which is 4. You can also perform basic arithmetic functions in R. For example, let's create the vector x, blooper, and then multiply each value of x by 2 as follows. We can also perform additions. So for example, combine each element of x with the respective element in y as follows. We can also get the mod of 2. For example, here x percentage 2. Or we could perform integer divisions as follows with x percentage / percentage 5. You can also perform set-based operations as follows. So let's create x and y with the following elements, and then we can take a look at the intersection of x and y using the intersect function. We can look for differences between the elements of x and y with the setDiff function, and then we can get the union of x and y using the union function. To retrieve information stored in vectors, you can use the index position, which starts at 1, unlike other programming languages like Perl and Python, which start at 0. Or search for content using several different base functions, which we will see, such as which and Boolean operators, match, etc. For example, we can get the elements stored in the 5th and 2nd position of our character and numeric vector as follows. To search for elements in your vector with Boolean operators, such as equal equal, or not equal, or and, or, we could say which x equal 12, which essentially means where in x is the value 12 located. And what happens is that it will return the index position where it finds a match. In this case, it is 4. The which function functions by returning the index value where it found true for the test is x equal to 12. Blooper, let's see another example where we say x equals apple. So it's going to search x for the word or the string apple. As you can see, it returns false, 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 essentially meaning that it did not find any match, which when we use the which function will return integer 0, which essentially means that it found nothing. You can also use binary operators, for example, percentage in percentage, which essentially looks for a match. And so to do this, we would say which x match apple, and you see it returns the index. What's fun about the match operator is that unlike the x equal, where you're looking for one specific, where you're essentially testing one string or one value, the which function can be used with a vector. So for example, we could say, well, which x matches apple or 12, and or 12. And so it will return the indices where it found apple or 12, and or 12. Alternatively, you can use the match function, which here we will use the string apple and comma x, which essentially says match apple in x. And you can see it returns the index. However, you need to bear in mind that the match function will only return the first instance where it found a match, unlike when you use the which and the match operator, which will return all instances. For example, let's create a new vector, z, and then we can ask which z match apple. As you can see, it returns both indices, whereas if we do match apple and z, it only returns the index of the first instance where it found apple. There are also other ways to retrieve the index position or to search for elements in your vector, and that is using regular expressions. So you could do this with the grep function, similar to grep in or grep in Unix. And so to do this, let's create a vector, so fruits, and then we will say grep apple in fruits. By fixing the fixed argument to true, it essentially searches for the string as is, and so it returns an index where it found a match with apple. You can also use regular expressions using the grep function. In this case, you will need to say fixed equals false. So let's say grep apple, open brackets, 1 or 2 fruits. And as you can see, it returns both indices where it found apple 1 and apple 2. Notice that if you keep fixed equals true and run this function, it won't return any values, because with fixed equals true, it will look for the string as is. You can also use the grep_l function, which is sort of similar to looking for a match, except that you're blooper. Then you can use the grep_l function, which is very similar to the grep function, except that instead of returning the index directly, it will return a logical vector of whether or not it found a match. So for example, let's do grep_l, and the little hat means, in regular expression, starts with the word apple. In fruits, and as you can see, it returns the indices. And blooper, as you can see, it returns true or false depending on whether it found apple. And then we can actually return the indices using the which functions like we did before. So which grep L starts with apple in fruits, and there we go. A faster version of this would be to use the starts with function, where you could say starts with fruits, apple. And then it will return where it found apple in a word that starts with apple in, or you could use starts with, where it will return true or false depending on whether it found a match, and we could use again the which function to return the indices for the matches. In summary, this video has shown you how to create and retrieve information stored in vectors, either by index position or using other practical R functions based on string matching or regular expressions. More specifically, we learned how to work with vectors of different classes, perform arithmetic and set-based operations, and search for vector elements by index position and other R functions. In the next video, we will learn how to create and manipulate list objects, attributes. In the next video, we will learn how to create list objects and attributes in R and learn how to retrieve information stored in these lists using index position and other key functions. So hi, and welcome with working with lists and attributes. In the previous video, we learned how to work with vectors, and now we will learn how to work with lists and attributes. In this video, we are going to take a look at the structure of lists, how to search lists by index position and name, how to add attributes to objects, and finally we will end with an example of how to use attributes with Venn diagram objects. So we'll start off by creating a simple list. So in this example, we are creating a list with the list function here with numbers 1 to 4. As you can see, the list is composed of 3 different elements. First, an integer vector, a number, a numeric vector, and a character vector that contains the word cat. A list can actually contain different types of objects. For example, it can contain a character vector, a numeric vector, it can contain a data frame. So a list can contain different types of elements. For example, it can contain, as we saw, an integer, numeric, or character vector, but it can also contain other types of objects such as a list, and as we will see, other types of objects such as a matrix or a data frame. So before we actually create the other list object, let's first create our logical vector. And now if we look at the structure with the str function, you see it contains 5 elements, where the last one is actually a list of 3 that contains an integer element, numeric vector element, and a character vector element. So now we can actually combine lists with the C function as follows. Now we can print out the contents of new list as follows, and as you can see, the individual numbers or of the vectors were coerced into a list of length 1. As you can see, 1, 2, etc. As a side note, you could delete the second example with new list, where I actually add the names A, B, and C to the different elements of this list. The example is around 7 minutes. You can get rid of that whole example and just jump to the structure of the new list. So it's actually quite useful to name the contents of your list as follows, and jump to the example at about 8 minutes and 20 seconds. So now we can coerce a vector into a list by using the as.list function. So for example, let's create the object x and then store it as a list in x as list. And now we can see the structure of this new object, and you can see it's a list of 4 where each has a numeric vector of length 1. Now to access elements in your blooper, so now to access elements in your list, you can use the square brackets. For example, we can look at our simple list and we can look at the element stored in the third position by doing simple list single square brackets 3. You could also do the same thing by doing simple list C, which also returns the value cat. So now we can look at the elements or the structure of the elements stored in symbol list at position 3, and as you can see, it returns a character string. Well, it actually blooper it returns a list of 1 with the character cat and the name of the element. Now if we use double brackets or double square brackets, you actually get cat itself, and then when you actually look at the structure, you see that it returns a character vector with the word cat stored in it. So this is important when you want to return objects stored in lists, since most of the time you want to return the object itself and not necessarily a list of that object. So you're more likely to use the double brackets to access elements in your list than the single brackets. As a second example, we can look at the structure of simple list double brackets 1, and you can see that it returns an integer vector. Blooper, this is also useful because you can actually store the contents of this list into a new object, for example, called animal, and as you can see, it returns cat. We could do the same thing again with the simple list double bracket 1 and store it in num vector, and then you'll see num vector returns the vector itself of 1, 2, 3, 4. Now we can actually look at the fourth element of that new object we've created, and it returns 4. So instead of creating a whole new object and then looking at specific elements, you could just do that directly by saying simple list double brackets 1 and then single square brackets 4, and it actually returns the same thing as num vector single brackets 4. And however, it's important to use double brackets for the first element, because or else you won't get what you're looking for, as you can see. If you were to use a single bracket notation, you could have written it as follows, but it's just way simpler to just use simple list double brackets, for example 1, and then the fourth element by doing a single bracket 4. So now let's look at attributes. So we can create an attribute by using the attr function. So for example, let's say for x as list, let's create a new attribute and then store this list contains the number of apples eaten for 3 different days. And now to actually see the attribute, new attribute for x as list, we could just simply write attr or use the attr function as follows. If we look at the structure of our x as list, then you will actually see the attribute appended at the end. So now we can actually create or add an attribute to our vector using the structure function, that is to say structure completely spelled out instead of the str function, and add the attribute as follows. So R also has built-in attributes such as class, dim, and names. So for example, let's create a list y as follows, and then look at names y. You can also change the names as follows by creating an element names object that contains first, second, third, and fourth, and then appending those names to y as follows. You could also use the set names function to add the names to your vector of interest. For example, so instead of first, second, third, and fourth, we can use alpha, beta, omega, and psi. We can check that it's been changed. So we can check the names of y by using the names function, and as you can see, it hasn't been changed. So in this case, we would need to say y and then adjust set names y and then c alpha, beta, omega, and psi. And then you can actually check the contents of your list by saying y double brackets beta, and it will return the value stored in the second element of y. So now we'll just conclude our example with a specific example looking at Venn diagrams, or how to retrieve information stores in different Venn compartments. So for this example, we're going to create two objects, so genes condition A and genes condition B, where we're naming genes 1 to 300 in the first and genes 150 to 500 in the second. And then we're going to use, and so now let's load the Venn diagram library and create a Venn list, and then get the Venn diagram using the Venn.diagram function and store this in Venn.plot, and then we can actually draw or create the image for this Venn diagram using the grid.draw function. And finally, we could use the Venn function part of the gplots package to actually look at the contents in each Venn compartment as follows. So now if we look at the structure that we've created for the object we've created with the Venn function A, you will see that it has a Venn compartment and has, looper, and you will see, and so you will see that this object actually has useful attributes such as condition A, the intersections attribute, which is a list of 3 that contains condition A, specific genes, condition B, specific genes, and genes that are part of both A and B. So now let's add the attribute to a new object called inters, which now actually, if you look at the structure, just shows that it's a list of 3. And then we can store these specific genes by doing inters $ condition A for the A specific genes, and then similarly for the B specific genes by doing inters $ condition B. By using the $, we're actually creating an adopt looper. We are actually creating an atomic vector that is then stored in the A specific object or the B specific object. And then if you look at the head of B specific, you'll get to see the first 6 genes that are specific to your condition B. Alternatively, you could use the lapply function to actually summarize the contents of each list element with the lapply, inters, and then the head function. So lapply is actually a quite useful function, and we'll learn more about this in the next section. So in summary, we've learned to look at the structure of lists and how to search for elements that are found in the list, and we learned how to add attributes and use attributes to get useful information from your list objects. And so in the next video, we will be looking at how to work with multi-dimensional arrays and matrices. Blooper, how to look how to work with multi-dimensional arrays and matrices. Thanks again, and see you in the next video. Hi, and welcome to Working with Multi-Dimensional Arrays and Matrices. In the previous video, we looked at how to work with lists and attributes. And now we are going to take a look at how to create and work with multi-dimensional arrays, matrices, and how to retrieve information by index position and use attributes to examine and or change array and matrix properties. Let's begin by creating a multi-dimensional array with the array function. In this example, we are going to create a three-dimensional array that contains the values 1 to 16 with the dimensions 2, 8, and 2. So create it and then look at the contents of the object. Oh, sorry. I would say we're going to, a 3. So if you look at the three-dimensional array, you have the first dimension, second dimension, third dimension. So 2, 8, 2. You could also create a multi-dimensional array using the dim function. So dim is just dimension. So for example, you can append or you can add you can create a vector with a sequence function. So sec from 1 to 12 by 2. And if we look at the values, we get 1, 3, 5, 7, 9, and 11. And then we could change the dimensions of this object with the dim function. So now we're making it 2, 3. And so when we print the values, you see that it is no longer a vector, but a matrix of dimensions 2 by 3. We could also, for example, have the dimensions be 3 by 2, in which case we do dim values C 3, 2, and then if we print values, you see it returns this matrix. Now, to retrieve elements by position in a multi-dimensional array, you need to obviously take into account the position. So, for example, if we go back to our coordinate object, and now we say print the first element of the first dimension. Well, not the first dimension, let's print the first dimension, sorry. If we go back to coordinates, it's actually returning these values here as a matrix. Now if we do coordinates 1, 2, we receive 1 and then 1, 2. 1, 2 is 3. And then finally if we look at coordinates 1, 2, 2, it's 3. So 1, 2, so 1, 2, 2 is 3. Now, let's create a matrix using the matrix function. So in this example, we'll create a values matrix with the values we had stored earlier and give it 3 columns and 2 rows. Now if we print the contents of this object, you see it returned what we had initially stored in values, but as instead of 2 columns and 3 rows, we did 3 columns and 2 rows. Another thing to remember is that as it entered the values, it went 1, 3, 5, 7, 9, 11. So 1, 3, 5, 7, 9, 11. Now let's create a matrix using 2 vectors. So for example, let's create vectors x and y as follows. And then we could use the rbind function to bind each vector as a row. In which case, if we inspect the object, you'll see x and y. We could use the cbind function, alternatively, if we wanted to combine these 2 vectors as columns, as follows. inspect the object, you see column. Now, if we were to retrieve elements stored in a matrix by position, we could do so, for example, in our values matrix, which if we reprint what it looks like, if we go values matrix 2, 2, so 2, 2 is 7, we should return, we get 7. Matrices and arrays are also indexed by like a vector, so which means that you could, instead of using the two values, you could alternatively, though it's very rarely done in R, is, for example, let's repeat values matrix, but then only use index position 4. And it also returns 7. And that's because the way it would read the vector from a matrix would be 1, 2, 3, 4. You can see this by saying, well, let's look at 3, see, which is 5, 2, 3, and 1. Similarly, you could do this the same with coordinates or multidimensional arrays, which if we use our coordinates examples, 3 returns 3. So it will go 1, 2, 3. It returns this value here. Now, since matrices and arrays are indexed as a vector, you can use the len function to determine how many elements are present in your matrix or array. For example, let's do length coordinates. And it returns 32. There are 32 elements. This property comes in very handy when writing for loops, as we'll see later in this chapter under flow control. Another useful function is the nrow and ncall functions. So nrow would return the number of rows, and ncall, for example, so number of columns, would return the number of columns. So for example, ncall 3. We can also do nrow here. It returns 2. Another useful attribute is the call names function, which in this case, for example, we can look at our values matrix, and then as you can see, there are no column names. So if we do call names, you get null. However, we can add call names using the call names function, as we would the names function like we saw with vectors. So for example, we're going to use column A, column B, column C for the call names. And now, if we print values matrix, you will see that it now has these column names. You could also do the same with row names. For example, you could do row names values underscore matrix and say C, A, B. And now, if we print values matrix, now we've named the call names, but we've also named the rows A and B. So this is to change the row names. Next, we can get the dimensions of an array using the dim function. Sort of similar to how, we created a multidimensional array with the dim function. So here it returns 2, 8, 2 for our coordinates. We could also change the names of these of the multidimensional array using dim names. However, in this case, instead of just providing a simple character vector, we will provide a list with the names for each dimension. For example, here, remember we have 2, 8, 2, so for the in the first dimension, alpha, beta, then the 8 will be named A through H, and then the 2 will be, these two will be called X and Y. So now if we print coordinates, we will see these names, and as you can see, it's x, y, alpha, beta. Sorry, so first, second, third, sorry. Okay, so this will be corrected in the actual audio. So first, second, third. So first. Now, for example, you could use the as matrix or as array function to convert, for example, one type of object to another. In this case, we will take a vector, x, and convert it to an array. To a matrix first. As you can see, it's a matrix with one column. Or we can do the same, but as an array here, where, as you can see, it's a one-dimensional array. Lastly, so you need to be aware that even simple vectors can be stored in multiple ways in R. So in the last example with the as array, you can see that it doesn't look very different from a vector, but in fact they are different classes. So a good example of this, for example, is let's look at the structure of x. As you can see, it's a numeric vector. If we look at the structure of array x3, it's a one-dimensional array shown here by 1D. 1, 6, 12. So if we print out what that object actually looks like, it looks like this. Okay? And then let's create a matrix with x. So this is a matrix of one column. And here we'll do the same, but with n row instead of n col equals 1. And if we look at the structure, you'll see now it's again a matrix where instead it's 1, 1, 2, 3 instead of here 1, 2, 3, 1. So these are the number 3 for the number of rows, and then at one column. So we have learned how to create multidimensional arrays and matrices, and learned how to retrieve information stored in these objects either by index position, or by index position. Now in the next video we will learn how to work with data frames and factors. So thank you for watching, and see you in the next video. Hi, and welcome to Working with Data Frames and Factors. In today's video, we are going to learn how to work with data frames, factors, and how to use the subset and by function to manipulate data frames. We will also take a look at the data tables package, which is a great way to subset information that you would otherwise store in data frames. Now let's begin by simulating an expression matrix data frame. So let's begin by loading an example into R. In this case, you will need to read the delimited files example 1.1-5 express matrix. If you do not have this file, you could generate this file as follows. So we will learn more about this in our second course, but essentially we'll be using the biomart package to simulate gene names, and we're going to use the rnorm function, which again you will learn in the next section, to simulate random normal numbers with the various means and standard deviations I've explicitly expressed here. So let's see. So here I'm just going to generate the expression matrix file in R directly. You might not have the exact same gene names if you did not necessarily use the same seed, or if you forgot to set the seed. Okay, so now that our example expression matrix that we've generated is loaded into R, we can start with our examples, looking at how to manipulate and work with data frames. So first, let's check the class of the expression matrix that we've generated. So in this case, it's a matrix. If you use the read.delim to load the file into R directly, then it would return a data frame, because that's what that function does. So if that was the case, if you generated this matrix by entering the code, then you're good to go. Otherwise, if you've entered the code using a text file, well, then you can just convert this express matrix to a data frame. Now, let's create a data frame from the expression values where each gene is a column and the sample that are rows are transposed using the transpose function, which is a T in R, and then convert it to a data frame as follows. So let's call it Luke data. So leukemia data. And if we look at the contents of Luke data, for the first 3 columns only, you will see here are the first 3 columns, and then now the leukemias are the row names and the genes are the columns. And if we check the class, you will see that it is indeed a data frame. Okay, now let's add the sample names to the call names of the expression matrix, which were lost when we please edit out this part and just continue from here. So now let's create so to do so, first let's create a vector, a character vector that essentially contains the types or subtypes of leukemia we're dealing with in this example. So for example, if our first 3 leukemias were ALL and our last 3 leukemias were CLL, let's use the repeat function to create a subtype vector. So in this case, so repeat ALL and CLL each 3 times. And as you can see, that's what it did. And if you check the class of subtype, it's a character vector. Now we need to convert that to a factor. So a factor is a much more efficient way of working with lots of functions in R. Instead of using characters and matching strings, factors are a lot more efficient. And so here we're going to use subtype, and then we're going to create, so each factor has levels. So we're going to create a factor, subtypes, Luke subtypes, with 2 levels, ALL and CLL. Now if you look at the contents of this object we've created, you now see it's a factor because it enumerates, you know, the name of the factor, and it also tells you what levels are present. So in the event that, for example, you didn't, so in this case we specified levels is equal to ALL followed by CLL, but if you were to exclude the levels argument, it often just goes by alphanumeric order. So that's something to bear in mind, because often when you work with a lot of functions that use factors, they will often use the first level as the reference level and the followings as samples. For example, in differential expression. What if you didn't want your levels to be ALL and CLL because you don't want your reference to be ALL? You could change them as follows. So let's say leukemia subtype B, where now the first level is CLL and the next one is ALL. And if you look at the contents, you'll see this part hasn't changed. It's just the order of the levels have changed. So now you have CLL first and ALL next. Instead of recreating a factor with the and changing all the levels, changing the levels you could potentially reorder the factor levels using the following code. So for example, let's use, for simplicity, say x is equal to leukemia subtype, and then, so instead of re-specifying factors, subtype, levels equals, etc., you could just simply say factors x, levels x, c, in brackets c to 1. So you're essentially changing the order of the factors. And now if we inspect our new leukemias B, well, it's exactly as what we wanted. So CLL is now the first level, and ALL is the second one. Otherwise, if you just need to change the reference, as I was saying, the first level, then you can use the relevel function as follows. So relevel, reference CLL, and now if we look at the contents, it is indeed CLL, the first level. Now, you can update a data frame with a factor. Essentially now you can update your data frame and add an extra column now, in addition to the gene names that specify the leukemia subtype as a factor. And so to do this, we will use a cbind function, sort of like what we saw earlier, where we use cbind to combine two vectors. You can use cbind to combine a data frame and a factor to create a new data frame. And now if you look at the structure of data, our data frame, you'll see that it has all the gene names plus now an extra column called subtype which is a factor with two levels, ALL and CLL. Now we can subset, for example, our data frame and to only look at the ALL samples. So let's do this by saying ALL data is equal to subset Luke data by, and here we're specifying the subtype is equal to ALL. Now be sure you use the equal sign, because that test is a logical, versus if you just say subtype equals equal, you're essentially replacing subtype with the string ALL. As you can see, now we have subset our data frame so that our original data frame Luke data by ALL subtype. We could do the same, for example, with CALL, but this time, instead of subsetting the whole data frame, just take, for example, 3 genes, EMP1, PRCC, and AQP3. Again, using the subset function and then setting subtypes equal CLLL. Oops, in this case we got an error. So, I need to check. It says we have an undefined column. Oh yes, that's because when I regenerated the data, I randomly chose different genes. So instead, let's say, just pick 3 genes from your data frame. So in this case, let's say NECAP1, ATPF5, and WNT11. Okay. Okie dokie, and rerun the code. And now you can see we no longer get the error message, and we have our new data frame subset by CLL and only for these 3 genes. Instead of using the subset function, which is quite useful, but sometimes, it might be simpler to use the by function, which essentially says, so by allows you to specify the factor to be used. So here we're saying here we're using the data Luke data, so this is the data frame. Then I want you to subset using the factor Luke data subtype, because Luke data subtype is essentially a Luke subtype, the factor that we created. And here it allows you to apply a function on your data frame by subtype, so by level of this factor here. And so instead of using these 3 genes, again, we'll have to change them. So here I'm just going to copy paste. As follows. And now, as you can see, it has subset So essentially you're applying this function, so which we've defined as function x is subset x select these 3 genes. But now it's done so by subtype, so ALL and CLL separately. So that's a useful tool to have, because with the by function you can literally, for example, apply whatever function you're interested in applying to each individual subset or each factor present, or by factor essentially. For clarity, instead of using the Luke data $ subtype, which is essentially the same thing as Luke subtype, we could have simply written the following. Again, we have to make sure we change these genes to make sure that we actually have genes that are present in our simulated expression matrix. So in this case, here we go. Like this. Oops. Sorry, made a mistake. Sorry about that. That's just weird. Okay. Please edit out this part of the video until I... Yes, so please edit out that part of the video where I kind of was like trying to figure out the error, and just start from here for the second part of the example. So essentially continuing from, so instead of using the previous notation, Luke data subtype here, we could have just simply used Luke subtype as follows. Okay, perfect. Even better, it gets a bit complicated, but we could have used the with function. So the with function essentially is almost like the attach function if you've already worked with R, but otherwise we'll learn it in one of the later videos, where instead of calling, so normally if you have a data frame, in this case Luke data, you could attach Luke data. And what this allows you to do is that if you look at the call names for Luke data, here they are. So instead of calling it, creating an atomic vector as follows, for example, wint11, you could just simply say wint11. If we detach Luke's data, you will no longer be able just to write wint11. You won't get it. You'll have to specify Luke data $wint11 to be able to get those values. The with function allows you to do something similar to the attach function. So in this case, you would have with Luke data. Say we wanted to print wint11, and it would do so. So essentially with the with function, you can take your data frame and then just call the call names as you would if you had attached the data frame to your our session environment. So another way that we could have written our by Luke data to be able to subset our by factor would be to use the with function as follows. So with Luke data, by Luke data subtype, because now I can just call this column directly, apply the function x subset x by selecting these three genes, and you get the same response. This is also the with function is quite useful in reordering, for example. So let's say we say with CLL data, order CLL data by the expression value of PRCC. Whoops, PRCC is not found because the gene is not expressed. So let's use this gene, or the gene is not present in our data frame, I should say. So here we go. And so now, as you can see, it reorders CLL data by the ATP5F1 expression levels. Another way you can work with data frames is to actually use the data table library, which is a quite efficient way to kind of subset and play around with your data as you would a data frame. So we've loaded the package, and now we'll have to change genes because, as I mentioned earlier, we are no longer working with the same genes. Here we go, and let's create the Luke table with the data.table function. So here I'm making a smaller table, so Luke table here, that essentially subsets the Luke data frame by these three genes, and then creates a data table with the data table function, as you can see here. So this is a table format, and then we could simply, instead of using that long formulation which we had shown earlier, we could simply use Luke table order by, instead of PRCC, you could say went in 11. And notice that you don't have to specify it's an atomic vector or attach. It will just automatically choose the right column and order the rows by the expression level of went 11. Another thing you could do is you can add a column to the Luke table with the mean expression of went 11. So instead of using PRCC in our examples, we'll change them to went 11 here. So here we go. So here we can order our Luke table by went 11 expression as follows. Okay, please edit out this whole part of the video, please. And start from data table. So another way you can work with data frames is using the data table package. So here we'll load it, and by doing so, it's a great way to efficiently work with data in R. For example, let's subset the Luke data object and create a data table with only these three genes. Okay. So if we look at the contents of this table, you can see it has our three genes of interest. And now we could, for example, order the Luke table by went 11 expression as follows. So as you can see, it does so nicely. Alternatively, we might want to, for example, calculate the mean of went 11, but by leukemic subtype. So ALL, CLL. And so we could do this easily with Luke table, create a new column that's equal to that has the mean of went 11 by leukemic subtype. The by function here takes a list. And so as you can see, now it has calculated the mean expression of went 11 by subtype. Next we can Sorry, I'll just change this to Wnt11. We can just look at Wnt11 expression across the samples as follows. Or we can take the mean of the ALLs as we would here, and you can see that it is indeed 3.286007. And similarly, we can test our so we can test our CLL mean as follows, and indeed it's 3.18. So data table is a great package if you're interested in getting summaries or manipulating your data table by factor. Notice that it does not write the row names, it just has them, but the row names are exactly the same as what we had in our Luke data. So let's see if we can say row names, sorry. You see it's invalid. Sorry, so please ignore this part of the video. Please remove this example, this last example with the error message. I'm just trying to figure out if it's possible to add row names. Sorry. Okay, yeah, no, you can't add row names, so please do not add this last example that I just added. Thanks. In this video, we learned how to work with data frames and factors, and how to subset a data frame by elements with the subset and by function. And finally, we went over how to use the data.table R package with then we learned how to use the data.table R package to work with our data more efficiently. So actually, I'm just going to change the text here, so please do not use this version. Okay, so in summary, in this video we learned how to work with data frames and factors, and how to subset data frame by elements with the subset and by function, and how to use the data.table package to more efficiently work with our data. So in the next video, we will learn how to load and save different types of data files in R, including text files, CSV files, Excel, and JSON files. Thank you for watching, and see you in the next video. So hi, and welcome to Loading and Saving Data in R. In this video, we are going to cover how to load data from R, objects or other formats, how to load Excel, SPSS, and JSON files into R, and how to save data as R objects or other formats, and how to save data as Excel sheets in a workbook with the write_xls package. Okay, so let's start. To be able to follow these examples, you're going to need to download the files that are available on our website or on my GitHub page, which is examples 1.6 tumor measurements and different file formats. Or if you'd like, you can just use your own files. Just be sure to change the file name. Also, don't forget to set your working directory either with the setwd function, where you then have your path in brackets, or manually you could go in RStudio and change the working directory, so to make sure the files are actually there. Okay, so let's start. So the simplest and most often used way there are several ways to load data into R. The most common way is to enter data using the read.table function, or one of its derivatives, the read.csv for CSV files and the read.delim for text files. Here we will use the example file example 1.6 _ tumor measurement.txt available on GitHub. For example, we can load this data into R using the read.table function as follows. So let's just copy and paste the code. And here you see it's read.table, the name of the file, followed by, so we need to indicate what the separator is with the SEP argument. So sep equals backslash, or is that forward slash? I have to double check if it's backslash or forward slash. Yeah, no, backslash t, which essentially means tab. And header equals true because in this file we happen to have a header. So as you can see, it loads each column here, and there are no row names. If you want to specify row names, then you will need to use the row.names argument. So in this case, row.names we set equal to 1 because I'd like to use the sample.id as the row names. And again, I want to keep my headers as column names. So now you see, we now have used, we get more or less the same data frame, except that this time we have the row name set to our sample IDs. Now, another thing that's quite useful is that when you use the read.table function is that it automatically generates a data frame and it will automatically convert strings into factors. So you can see this by looking at my data as follows, where you can see here tumor width is an integer, tumor length, tumor volume, and tumor type is actually a factor with 2 levels A and B. So in the event that you wanted to maintain your strings as factors, you would need to specify the strings as factors argument as false, as follows. Okay? And then after that, there are other, like I mentioned, other functions you can use to load your data into R that are derivatives of this function. So, for example, we could have just simply used the read.delim. Again, all the arguments are more or less the same, except this time you don't have to specify the separator as \t because it automatically uses tabs, but all the rest is the same. So here you go. And another useful function is the read.csv. So for this example, let's first load our CSV file using the read.t table. Again, the file name is the same except the ending is .csv. And if you wanted to use the read.table, you would need to specify the separator, which is in this case is a comma. And then you see it loads. Otherwise, you could just directly use the read.csv function as follows. So again, all the arguments are the same because we want to keep our strings as characters, not factors. We use the string as factors equals false. Now, to load Excel sheets within R, you can use the GData package. So make sure this is downloaded and installed on your computer. And so let's load our GData package first. Okay. And then now let's read our XLSX file. Again, everything is the same except now that we don't need to add a separator. We just need to specify which sheet. So you can specify the sheet either as, by its number or by the sheet name. And all the other parameters will keep the same. And as you can see, it returns our data frame. Alternatively, you might want to use the XLC Connect package, which will also allow you to load worksheets into R, Excel worksheets into R. So let's use this package instead. Okay. And now, it's slightly different in that you first need to load to create load a workbook itself. So let's say my workbook is, and then we use a load workbook function and ask it to load this file. It takes a little time, and then after that you could say, well, now I'd like to read my worksheet and store it as data frame. So we use the read worksheet function. And then you see my worksheet. You need to specify, my workbook, the object with the workbook.
which sheet, and then, here I specified that I'd like to use the first column as row names. Note that row names is all in one word and not row dot names for this function. And if we look at the contents or how it was loaded, it looks like this, same way. Note that here in this case, your strings are factors, and this you can see here. Oh no, actually it loads them as characters. Sorry about that. So that's quite useful. So you don't need to specify right off the bat that you don't need to specify the beginning whether or not your string should be maintained as characters or converted to factors. There are other really useful parameters with the XLC Connect package when you're loading your worksheets. For example, you can actually just pick which columns you're interested in loading directly instead of loading the data frame and then subsetting your data frame. So for example, here we can say, well, start call 1 and call 3, and my row names is still call 1. So you see, it loaded all from 1 to 3, and then it used it used number 1 as the first column as the row names. Now, the other ones will just be for demonstration purpose only. So, for example, you might want to load your SPSS files directly into R. And again, these won't run, so but feel free to use them if you work with SPSS files. So you could load the library forward and then use the read.spss file. So for example, if you had a file, so in this case, like I said, it's just for demonstration purpose only, but you could use read.spss, your file name, and then you ask it to convert it to a data frame. Otherwise, you might be interested in working with JSON files. Again, this is for demonstration purposes only, but you could load the RJSON library, and then after that, load the data into R, first as a list of vectors, and then after that, you could convert this list of vectors into a data frame. So feel free to try to load your JSON files into R as well. And now another useful way of saving objects instead of so before going into how to load objects, let's okay. So now, before learning how to load objects into R, let's first save our objects using the save function. So in this case, let's create two objects, x and y, where x is a vector of 1 to 139, and y is a matrix of 1 to 20, a 4x5 matrix. And now we can save both objects with the save function, and then as we need to specify the file name, so file equals, and we'll call it example data.rdata. So now, the next time we could just load both objects at the same time using the load function. Example here. Okay. And now if we use ls to list all the objects, you'll see it has x and y present. Alternatively, sometimes working with really large objects can take a long time to save or a very long time to load. So I like to just save them directly using the save RDS function. But when you use this, it saves the you have to save one object at a time, and when you reload the object, you will need to specify you need to put it in or create a new object and load that object into that new object that you've created. So, for example, we could save x and y separately as with the save.rds function. I think it helps to name them with .rds at the end so you don't mix up your file types. And then if we were to reload, for example, x from the save RDS or the x.rds file, then we would use the read read RDS, and you would need to store it into X2 or a new object, or restore it into X, for example. This is important because if you just do read RDS, it won't just save it in your environment. It's just going to print the contents of the object. So to save data into R, blah blah blah, I'll re-go over what I just said and show the example. And then, so now in your working directory, you should have a copy of this data saved as savedata_file.txt that you can open. So when you do this, you'll notice that by default, if you were to open this in Excel, you would have something that looks like this. Essentially, you see the row names, but the call names are actually shifted or not shifted appropriately. So to fix that, you could use the write.table, but instead in this case you would specify call.names is equal to NA, and then row.names equals true. And when you do that, if you reopen it into Excel, you will see that it's has corrected the shift, the inappropriate shift. Otherwise, like I mentioned, you could use the write CSV function. Again, it's the same content. You'll find a copy of this in your working directory, and you'll be able to open it in Excel or any other spreadsheet viewer. Now, if you have multiple data frames, you might find it more interesting to actually save it directly as an Excel worksheet or workbook. Sorry. So you would like to save each data frame as a worksheet in a workbook directly. And so let's create two data frames. So here you can see the context of df1, df2, and now we will use the write XLS library to be able to create our workbook. So first you store the names of the data frames that you would like to save into an object. So I've just said dfs.toSave. Then I need to specify the name of the sheets to save, which are in this case df1 results _ results, df2 _ results. And then I use the write XLS function with the dfs to save. The Excel file name, I'm going to call it combined DFS workbook.xls, and the sheet names is going to be sheets.tosave. Use sheets.tosave. And then in your working directory, you should have an Excel workbook that has each one separately, stored as separate sheets in your workbook. So very useful tool to have or to know. So now in summary, I've just shown you how to load data from R from different formats. I've also shown you how to save data in R and how to use Excel packages or packages that enable you to save and load data from Excel worksheets directly. And now, in summary, since this is the last video of this section, I just want to summarize what we've learned so far in this section is how to work with vectors, lists and attributes, multi-dimensional arrays and matrices, data frames and factors, and how to load and save data in R. And in the next section, we'll be looking at how to manipulate our data sets in R using various functions and tools that are quite useful when working with bioinformatic data or just general data. So thank you very much. And I look forward to seeing you in the next video.
So hi and welcome to Fundamentals of R Programming. In this section, we're going to be looking at how to manipulate data sets with R. And so in this section, we're going to take a look at several functions, including the subset and width function, the which and grep function, the sort and order function, the sapply and lapply function, and finally the tapply and table function. In this video, we're going to be looking at how to work with the subset and width function. In this video, we're going to take a look at the basics of the subset function and explore data with this function, and the basics of the width function, and again look at some data on how to use the width function. So for our first example, we're going to create a vector x as follows, and then we're going to use the subset function to retrieve all elements in x greater than 5 as follows. This is the same thing, or this is similar as using the brackets notation as x greater than 5. So you notice here that when we use this notation instead of the subset function is that the NAs are kept, whereas if we use the subset function, the NAs are removed. We can also use the subset function on a matrix. And for this example, let's create a simple matrix, mat1, with 4 rows. Let's add the column names, A to E. And finally, look at the head of the mat object as follows. We could subset this matrix by column name as follows. So here we could use subset and the select argument to select the column C, D, and E as follows. We could also use a subset function with data frames, and for this example we're just going to take advantage of the air quality data frame, which is available in the base R package or automatically available to you in R. And as you can see, it has several columns, namely the ozone, solar R, wind, temp, month, and day column. If you look at the structure of this data frame, well, you see it is indeed a data frame composed of integer and numeric vectors. So now let's subset this data frame by the solar R values greater than 300 and then remove the columns ozone and temp by using the negative sign here. And as you can see, we have separated the air quality data frame based on solar R values, and again here we have removed the ozone and temp columns. We could also subset, for example, by day. Say we only wanted the rows where the day was equal to 1. So here we need to use the Boolean operator equal sign, and then again we use select equals minus ozone and temp to remove those 2 columns. And as you can see, we have successfully subsetted our data frame. Now for the next example, looking at actual biological data, let's load the expression values in our example 2.1/1 express data.txt file, which is available on the website. And here we can take a look at the contents of this object by using head, and then if we were interested in the structure, we could use the str function. So you see it's a data frame. Now let's say we wanted to get the expression values for the call for a gene in all samples. So for this, let's convert our express data frame into a matrix. So just to remind you what our express PRS for expression data frame looks like, you see we have the gene call A here, and we have 3 ALL samples and 3 MLL samples. And then we are now going to convert this so that the column names are the gene names as follows with the transpose, so the T function. So you can take a look at what this looks like using the head function. As you can see, now the rows are the samples and the columns are the gene names. And then let us subset our gene express matrix by selecting our gene of interest called for A2. And now if we take a look at this object, so if we take a look at that object here, we can do head, and as you can see, it contains, let's ensure that it's a data frame by using the as.dataframe function. And then here we're saying that we want call4a2 to be greater than 3 now. If we actually print, you see that it returns all the samples for which the gene level is greater than 3. Now let's look at another example where we subset our gene expression object, so gene express, with the subset function, and this time selecting 3 genes, the call4a2, ATP5F1, and Wnt11, using the select function. So now, say we wanted to, again, only retrieve the samples where call4a2 levels were greater than 3, we can now apply the subset function. Again, first making sure that it's a data frame so that we can just call the column names. And as you can see, it returns the samples of interest with the columns of interest. In the previous example, we went through 2 steps. So we first created this call4a2 greater than 3 object, and then we created our canned genes object because we selected the columns we were interested in, and then we applied the filter call4a2 greater than 3. But we could have written that simply all in one step as follows. So here subset as data frame because our gene express is a matrix where the call4a2 values is greater than 3, and select these 3 columns. And as you can see, it returns the same result. So I just wanted to break it down into multiple steps, but as you can see here, you can write it in one line of code, which is probably better. So now let's look at some examples with the with function. So let's first take our mat1 matrix that we created earlier and then transform it into a data frame. And then let's look at the contents of our data frame that we've just created with the head function. And as you can see, here we go. Looks good. Now with the with function, we can just call the data frame, say with data frame mat1df, I would like to subtract row A from E. Okay, so E minus A. And as you can see, it returns the values 44444, which is the case. We could have added this E minus A to a new column in the mat1 data frame as follows. And here we go. So here now we're saving it into the mat1df, you see, and now I'm using the $sign to say create an atomic vector in this object called E minus A. And as you can see, now we've added it as an additional column. Otherwise, we could have used the cbind function instead of just using the $sign with the E minus A atomic vector that we create as follows. Okay, so you see here it's just adding it on top, but you see here we again created a E minus A vector from the with function where we subtracted E from A, and then we bound the mat1df with the E minus A vector with the cbind function. And since mat1df is a data frame, cbind assumes it's a data frame and not a matrix. And, or alternatively, we could have written it as one line of code. So let's recreate our mat1df. And this time we could have done it in one line of code as follows. So here we do cbind mat1df E minus A is equal to, so here we're creating the vector E minus A with mat1df E minus A. And then I'm just using the head function to show you what the results look like. So now, using our biological example, say we wanted to create a function that converts the log expression value, sorry, this should be value, to the original value. So let's create a function here that we call retransform value, which is function of x where it's 2 to the power of x. So this is our retransform function. Now, let's convert our gene express, which is a matrix, to a data frame as follows. And then let's use the with function to retransform the values of Wnt11. So here it's again with gene express df. Let's apply the retransform function on the Wnt11 column. And as you can see, it is retransformed the values. We can check our results as follows. So let's save the results in a vector y and then look at log2y. And so if we look at y, it's the results above, and log2y is these values here. And if we look at the original values, which were in log2 expression, they're the same. So it worked. So to conclude, in summary, we learned how to use the subset and width functions with vectors, data frames, and matrices. And in the next video, we'll be working on how to use the which and grep function to search for the indices or elements in our vector data frame and potentially other types of R objects. Thanks. Hi, and welcome to Fundamentals of R Programming. In today's video, we will be looking at how to work with the which and grep function. So, working with the which and grep function. In this video, we are going to take a look at the basics of the which function and explore some data using this function. And then we're going to look at the basics of the grep function, and then again look at how we could explore some of our data with the grep function. Okay, so let's start by creating a logical vector, which we will call logical vector, which contains true, t, which is true, false, 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 and true. And so, if we use the which function with the logical vector we just created, it will return the indices where it found true. So, if we look at this in more detail, we could say logical vector and show me the results at the end, show me the contents at true indices, and you see that it returns true, true, and true. If we look at what the which function returned directly, it returned the values 1, 2, and 7, which meant that the first, second, and seventh element contained the true. Next, say we wanted to return the indices or the contents of the logical vector that were false. In this case, we could say logical vector minus true indices, in which you see it returns false, 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 false. Now in our second example, instead of using true and false, we could potentially create a logical vector using ones and zeros. 1 for true and 0 for false. So let's create another logical vector, but in this case, because we don't want our values to be considered as integers, we will use the as logical function. And so now if we say which ones were true, again it will return the indices where it found true, so 1, 3, 4, and 5. You can, for example, what if you wanted to know which ones were false? In that case, you would need to use the negative or not operator, which is the exclamation mark. So which is not logical vector. Which ones in logical vector is not, so is false essentially. So you see it's 2, 6, and 7, which had zeros. Alternatively, if we wanted to use the which function, we could say logical vector 2, which elements are false in logical vector 2, and it will return the 3 falsest that were there. Now let's look at another example working with Boolean operators in this case. So let's first create a vector x here that contains these values, and then we will say, well, I want to return elements of x that are greater than 100. And so when you just use the greater than sign, it actually returns a vector of true and false depending on whether or not element of that vector made the requirement essentially. And so as you can see, it's only the 2 last elements that were true. So since the which vector essentially allows you to return the indices that were true, or if you use the exclamation mark false, we can say which x greater than 100, and now it returns the indices 13 and 14. To see what are the values where the which function found trues, you can again say x, which is like which x is greater than 100. And there you go. Okay. Now let's look at a practical example looking at gene expression data. So from here. So in this experiment, we measured some protein, and in this case, we measured actin. And so the values here are in micrograms, and we stored in the actin vector. Then let's create our sample groups. So our first one is sample tissue, which is a mixture of spleens and bone marrow. And lastly, we're going to have the sample numbers, which are M2179, etc. And we want to repeat each one of these values 3 times. Okay, now let's create a data frame from the 3 vectors we just created as follows. So see, and we add the argument strings as factors equals false because we don't want to convert our strings here, such as a sample number, into a factor. Okay, now let's create a function to test whether our sample matches a given tissue and sample number. So for example, say I was interested in returning the lines where actin amount found for M2179 spleen. So we're going to write a simple function to do this. So here we're going to call our function test tissue sample, function x tissue sample number, and then the function actually tests whether first if the first element of x is equal to our tissue, which is defined by our tissue argument, and since we're testing, we need to use the Boolean version of and, which is 2 and. X second element is equal to our sample number defined by our sample argument, then return true or else return false. And now look at the head first of our actin DF data frame that we created. And as you see, if we just look at the first 2, so the second one here has spleen, bone marrow, etc., and then the third has the sample number. Now let's use the apply function to return the results from our test function as follows. So remember here that the x first element and second element is being used to test whether or not it's true or false. So it's very important that our first column contain tissue information and our second column contain sample number information, which is why we need to provide it directly with actin DF columns 2 and 3. We want to do the test by row, hence the one here, test tissue sample. And because we have arguments to specify, we then need to say tissue equals spleen, sample number equals M6765. And then we're just returning the object. So as you can see, by running the apply function with the function we just created, we now have a logical vector returned to us with false, false, true, true, false, 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 false. And so, say we wanted to know which rows actually contained the tissue, spleen, and sample number M6765, then we could use the which function as follows, where now it returns 4 and 5. Okay, since the which function actually returns indices, or the row numbers, then we could directly include this in our actin DF and then look exclusively at the data frame for these 2 rows. And as you can see, well, now our actin micrograms was 1208 in one case and 909 in the other. And you see it's returned both instances where the sample tissue was spleen and the sample number was the appropriate one we were interested in. So that's kind of an overview of how to use the which function. So as you can see, it can return indices, and these indices can be used to, either investigate your data frame, to subset your data frame, etc. Now let's look at the grep function, which is quite useful as well. So let's look at a simple example here where x is a character vector that has Zapple, Mapple, Apple, and Apple2. And then say we are searching, so grep essentially allows you to look for regular expressions, and in this case we're looking for the string apple in the vector x, and as you can see, well, it returns all 4 elements because it could find apple, or the string apple, in each element. Now it's important to recognize that it doesn't search for the word as is, it just tries to match the string. Let's say we wanted to look at apple2, so search for the string apple2. Well, in this case it only returns 4 because it's the only element where it could find the full string. Now, sometimes that isn't very useful because say we were really interested in words that start with apple. Well, in that case, we could use regular expression terms such as, for example, here, the little hat, or the other symbol, or the symbol used for exponentials, as you wish. By using this symbol, we are specifying that we want to match strings starting with apple. And here we need to specify fixed equals false so that it will allow us to use, will not search for the string as is, but we'll consider this as a reg expression term. So here now you see it returns apple and apple too, because both of these elements 3 and 4 start with the word apple, or start with the string apple. Now, what if we wanted it to end with apple? Well, then we could use another tool, which is the $sign here, which says, well, defines the end. So this means start and this means end. And now again, we need to specify fixed equals false so that it doesn't try to search for the string as is. And now you see it returns 1, 2, and 3 because all these 3 elements end with apple. Now, most of the time you want to search for words. So in that case, you could use the reg expression operator, not operator, but you could use the escape or \b to define boundaries. So here you need to use grep. You need to first use this / as an escape. So it says, so that it doesn't consider it, then \b, and then you need to end as well. So these, essentially this symbol defines your word boundaries. And so if you search as is, it will only return, in this case, apple, because you've set the boundaries so that it looks exclusively for apple, as is. Or starts and finishes with. Another way you could have written this is as follows, with grep starts with and then ends, and you see it returns the same results. So here you're using boundaries, which is you're defining with \b, and you need to put it at start and end, or you could just use the start or end. So finally, let's look at another example where we look at some biological data. So for example, say we define actin SAMS as the sample tissue with the sample number. So if we look at the contents of this vector we've created, well, we've now merged the sample tissue with the sample number separated by an underscore. And now what we could have also done, grep is then just search directly for spleen underscore M6765, and then it returns 4 and 5. If you want to be on the safer side, you could define boundaries because, as I said, it does string matching, but what if a part of your string is also present in another element? By doing so, you're sure that it just searches for the string and respects the boundaries you've predefined. So notice that I did not say fixed equals false because by default, grep has fixed equals false, which you can see at the bottom. Okay. And so, in summary, I've shown you how to use the which and grep function to be able to search for terms of interest or potentially return indices for elements where you can test the condition and it will return true or false. So essentially, in summary, I've shown you how to use the which function and the grep function to return indices for either strings that you found through pattern matching, as with grep, or using functions that return true or false to return the indices that where it found true with the which function. And so now in the next video, we will be working with the order and sort function. In today's video, we will be working with the sort and order function. More specifically, we're going to take a look at the basics of the sort function, how to reorganize data with this function, and the basics of the order function and how to reorganize data with the order function. And so now let's take a look at some examples. So in our first example, we'll create a vector x, and then we will sort the contents of this vector with the sort function. As you can see, it has sorted the elements from the lowest to the greatest number. So in ascending order. And if we were interested in sorting the contents by decreasing order, we just need to specify decreasing equals true. Okay? You can also sort character vectors. For example, if we have our fruits vector here, we can sort from A to Z with the sort fruits as follows. Alternatively, we could go and sort in decreasing order by specifying decreasing equals true. Now for our next example, we're going to reload the expression data that we had in video 2.1 and store it in the express object as follows. And so if you inspect the contents, you see that there are gene names here. These are the expression values across 6 samples. So let's say we are interested in creating a vector for MLL1, so the first MLL patient here. We could do so by specifying express using and then the $ to specify atomic vector MLL1. So now let's give it each row name. So each element of the MLL1 express vector, let's add names. So let's use the row name so we can include the gene names. And so what this looks like is, so you see now instead of having just the expression values, we also have the gene names that correspond to each expression value. And now let's sort our MLL1 expression values from high to low. Okay, as follows. So MLL high to high low. Let's sort MLL decreasing equals true. And then if we look at the contents of the object we just created, you can see that it has the gene most highly expressed as the first element and the one most lowly expressed as the last element. Now say we were interested in getting the top 10 genes or the top 10 genes by expression for the MLL1. We could take our MLL1 high-low object and then subset or get elements 1 to 10 and store it in a new object, which when we inspect, we see that it's the top 10 genes by expression from high to low. And now, say we were interested only knowing what the top 10 genes were, but more importantly, we're interested in returning the indexes of each of these elements. So we know already that call for A2 corresponds to the first index, right? So if we do this, if we go back to our original vector, we know it's the first element. So what if we wanted to know what each index element it was? Well, then we could use a sort function as above, but this time specify index.return equals true. And now when we inspect the object that we've just created, the MLL1 high-low object, now you see that it's actually a list with 2 names, X and IX. And in the first, we actually have our sorted vector. And in the second, we have the position or the index where this gene corresponds to in the original vector we used, MLL1 express. So instead of using the sort function to retrieve indices, instead of having to create a list every time, you could just directly use the order function. So when we use the order function, say order MLL1 express, it actually orders it by expression value. And then say, so this is by ascending, and then if we want it by decreasing equals true or descending, then you see we get back those positions, which is essentially the same index positions as when we use the sort function index.return equals true as follows. Usually we use the order function to sort data frames. So here we're going to take a look at a couple. For example, let's create an expression data frame for MLL1 ordered. So essentially order our expression data frame by the expression values of the MLL1 sample from high to low. So decreasing equals true. And so if we print the first 10 rows with the head function, you will see that here we've reorganized our expression data frame based on the MLL1 genes from high to low. Alternatively, we could use the width function to simplify our code as follows. So remember, the with function works with data frames. So here we're saying with the express data frame, instead of saying, we could write with express order, like we take the expression, order MLL1 decreasing equals true. So the advantage of using the with function essentially here is that we don't have to write this full line of expression atomic vector MLL_1. Okay? And so it's a bit more legible to read. So if we again just plot the first 10 lines, you see again it's been ordered according to MLL1 gene expressions. Notice that since the sort function had returned the index positions, we could have also just sorted or created or sorted our expression data frame as follows, using the MLL1 high-low $IX for the number of rows, and inspect the first 10 elements, and again it's the same results. The advantage of using the order function over the sort function is that you can actually sort your data frame by multiple variables. So in this case, say we were interested in sorting by MLL1 gene expression in decreasing order, and then by MLL2 expression in decreasing order. So to do that, we would again use the with function for simplicity, expression order minus MLL1 minus MLL2. So essentially the minus sign just is the equivalent of saying decreasing equals true. And so now we have the index position ordered by these conditions. And so if we wanted to create a data frame like we did earlier, we could just do expression the index position, so the ins object, and then we can inspect the first 20 lines as follows with the head function. And as you can see, we go up, it first sorted according to the expression level in ML1, and then in decreasing order, and then in MLL2, based on MLL2. But essentially, MLL1 kind of, since it organizes it based on MLL1 first, I mean, it's quite understandable that it's essentially redundant to keep MLL2 also organize vector by decreasing order of MLL2. It would only be useful if, for example, the values were actually integers, or where we had multiple 7s, 5s, for example, then it would take into account the values of MLL2 in setting that order. And so in contrast, so it's probably not the best example, but it's just to illustrate the code. And say now, if we were interested in saying having MLL1 in ascending order and then MLL2 in descending order, so sorting by these two variables, well then we could do the same thing where we first store the indices into the ins object, where order by MLL1 and then negative MLL2. And then we could again create our data frame as follows and look at the first, let's say 10 elements instead as follows. So here you see it's orders ML1 in increasing order, so from smallest to largest, and then ML2 in decreasing order. But like I say, it's not really useful since we're actually using with floating points numbers. But if it was with integers, for example, or in cases where you had multiple entries with the same value, then you would see the effect of sorting with both variables. So in order to get a better feel for that, let's use a simpler example where we create a data frame with lab members and their ages. So Matthew, Carol, and John. If we look at this data frame, you see first name Matthew, Carol, and John, and their age. And so now let's sort by age and first name. Let's say decreasing, so from the oldest to the youngest in age, and then from A to Z for the first name. And you see, so now it's set Carol, because she's the oldest, Matthew, and John, in contrast to what it was originally, where it was Matthew, Carol, and John. So you see we've done age in decreasing and then sorted by name. But again, it probably would be more interesting if we had an example where two people were the same age. So for example, if John and let's add Amanda are the same age. Okay. And now let's again with the with and order functions. And as you can see, here it's much better illustrated where we first sorted by age, so ordered by age, so negative, so oldest to youngest, and then by first name. So because Amanda and John are the same age, well, because Amanda is A and John is J, well, she comes up first. In summary, we've learned how to use the sort and order function to be able to reorganize our data and to sort our data frames based on multiple variables. And now in the next video, we'll be working with the sapply and lapply function, which allow you to work more effectively with lists and vectors. In today's video, we will be working with the sapply and lapply function. More specifically, in this video, we are going to take a look at the basics of the sapply function and how to extract meaningful data using the sapply function, and then the basics of the lapply function, and again, what are some of the advantages of using the lapply function to extract data from your objects. And so now let's begin by going through some of the examples. So in our first example, let's create a vector x as follows, where we repeat the sequence of integers 3 times with the repeat function. So if you take a look, that's what it looks like. And then let's create a matrix X with 3 rows. So again, matrix 1. And then now, if we wanted to take a look at mat1, there we go. And say we wanted to use the apply function, which is kind of the basics of where the apply, sapply, and lapply function. Essentially, these functions are all related to a certain extent. But the apply function is used on matrices or data frames. And here, let's say, well, I would like to apply, so look to get the sum of each row, so 1 indicates row, on mat1. And so if we do that, you see that each row adds up to 67. Now, what if we wanted to get the sum of each column? Well, we could apply the sum function, but this time by column, by indicating 2 here, and here we get 25, 54, 30, 34, and 50. Another neat tool with the apply function is that you don't have to use you don't have to use our functions. You can also write your own function directly into the apply function. So again, here we are creating a function x, where we're adding 2 to the value of x, and we're applying this function by both row and column, so at each individual entry in mat1 as follows. And so as you see, we've now added 2 to each element in the matrix. Let's use another example to actually now look at the sapply function. So the apply function really is designed to work with matrices. You can specify the number of rows, the number of columns, but the sapply and lapply function actually work with lists or vectors. So, but as you can see, it's a bit mostly used for lists. So let's now create a list of matrices as follows. So let's create matrix 2, which we're saying add the value 2 to x, and we're having 2 rows. So if you look at mat2, this is what it looks like. And then remember, mat1 looks like this. And now we're going to create a list with 2 elements, A and B, where A is matrix 1 and B is matrix 2. So let's take a look at the contents of this list as follows. And as you can see, A and B. Now, let's use the sapply function now to get the sum of all the elements in A and B. So one way to do this is to use the sapply function. So sapply, we specify the list, and then we say we want the sum. And so it returns in A, there was 201, and B, 203. And so it's quite useful, the sapply function, because it returns a vector. And in this case, a name vector, because our num list had names A and B. We can also, for example, use the sapply function to get the mean of the both element of our list. So each element in our list. And so the mean in matrix 1 is 13.4, and then the mean in matrix B is 12.68. Or more precisely, 12.69. And then in our last example, let's use the sapply function to get the median. And so you can see that here, really, it allows us to apply the function, but this time on a list of different objects. So for our next example, looking at biological data, let's load some tumor size measurements taken at day 20 and 60 in mice. And so let's load this data as follows. And these text files are available on the website. And then let's just get an idea of what's in these objects. Well, we could look at the day 20, and as you can see, it essentially has the sample name, the tumor width, tumor length, and then tumor type. And so we are now interested in calculating the tumor volume at not only day 20, but don't forget we also have measurements at day 60. So if we take a look, you see we have these measurements here. And if you look at the structure of this object, essentially you see it's a data frame where the first two columns are integers and the last one, the tumor type, is a factor. So now let's create a list containing the data frames for day 20 and day 60 and store it in experiment 1. So here we go, and now let's look at the structure of experiment 1. Well, you see it's a list of data frames where the first is day 20 and the second is day 60. And now to calculate the tumor volume, well, we're going to use the formula. It's length times width divided by 2. And so we create this function here where we say function x, calculate the volume, vol here, as the second element of x, which the second element of x will contain our length, the first element of x, which should contain the width, the first element of x should contain the width, and then it is essentially squared because w times w is the same thing as w squared, and the whole divided by 2. And then we return the volume we calculated. And so now we can apply, for example, our function to some test data. So here, in this case, we're saying that the width is 2 and the length is 4. And so our tumor volume would be 8. So now we can actually apply this function we've created on our data. So remember I told you that you could use the apply function with data frames or matrices. So technically, if you wanted to, you could just say, well, I'm going to take the first element of experiment 1 of my list, and remember I only need the width and length, so the first and second column, and then I would like to calculate the tumor volume by row as follows. And so it returns the tumor volume for each sample at day 20. And then for day 60, you would do the same thing, except that now you're taking your second element stored in experiment 1, which is you, and then it returns these values here. However, we could actually write this in 2 lines of code and use the sapply function as follows. So first, all we have to do is create a function for what we want to do to our list objects, which in this case we're going to call ff. And so the function of x, we're going to take, which x in this case will be a matrix or data frame. It will take x, the 2 first columns, by row, apply the tumor vol calc function. And so that's our function. And then we use the sapply function here on experiment 1 with ff, which is the function we've just created. And you see now it returns a nice data frame where you can see the tumor volumes for day 20 and the tumor volumes for day 60. Now, instead of the sapply function, the lapply function is also very useful because instead of returning a vector, or a matrix. So actually the sapply function in this case returns a matrix, which you can see here as a numeric. See, so that's a matrix. But the lapply function will return the answers as a list. So let's just look at a very simple example at first, where in experiment 1, say we wanted to only print the first 6 lines, like we did with the head function. Here we go. So here we're showing day 20, day 60, and it's printing the first 6 lines. So it's essentially returning a list of the answer. Now, what if we wanted to use the dim function? Sorry about that. So I'll apply experiment 1 dim. So you see it's returning the dimensions for the objects that we have in our list as a list. So if you actually look at the structure, you will see it's a list of 2. So now we could reapply that function that we created to get our tumor volume calculations, but this time instead of returning a matrix, return a list as follows. So here you see now instead of returning a matrix, it's actually returning a list where the tumor volumes are for the day 20 are stored as a vector, and for day 60 are stored in a vector, and these vectors are put together in a list. So in summary, what I've shown you is how to use the sapply and lapply function to be able to work with list objects, to be able to manipulate these objects using functions, and also we had a good review of the apply function and how to apply functions to matrices and data frames. And now in the next video, we'll be looking or working with the tapply and table function. So hi, and welcome to Fundamentals of R Programming. In this video, we will be working with the tapply and table function. More specifically, we'll be taking a look at the basics of the tapply function and how to explore data with this function, and then the basics of the table function, and again, how to explore your data using this function. And now, for our first example, let's create a vector heights that contains the heights of individuals that we've collected, and then their corresponding gender as a factor, where we specify the levels are male and female as follows. And then if we take a look at our gender vector, you'll see that it is indeed a factor where the levels are male and female instead of female and male by default. And then we can use the tapply function to actually calculate the mean of the heights by gender. So essentially the tapply function allows you to apply a function, mean, such as mean, to a vector by a corresponding factor. In this case, looking at the mean of height by gender. And as you can see, the male is 180 and the female 136.75. Now, what if you had some of the weights but not all of them? So let's create a weights vector, and here you have some NAs, and then say you were interested in calculating the weight, the mean weight of these individuals by gender. And so in this case, you will see that it isn't exactly what we want, because by default, the mean function actually has na.rm, so remove the NAs equals to false. So it won't remove the NAs, and so that's why we're getting an NA here. So in order to use the argument na.rm equals true, we need to add it as follows. So here we're applying the mean function to the weights vector by gender and specifying that the NAs should be removed as follows. So now for a biological example, let's load our tumor volume data, which is available as an R object on our website and on the website and here. So here we have loaded it, and then the object that should be loaded into your space should be the tumor volume day. And so if you look at the structure of this object, you see that it's a data frame where it has day 20 and day 60 volumes and the tumor type as a factor. And so if you'll recognize that this is essentially the data we generated in the previous video. So now for a simple question, what if we wanted to know the mean tumor volume at day 60 and day 20 by tumor type? And so what we could do for each one is apply the tapply function. So here we're saying we're getting the atomic vector with a date for day 20 from this data frame. And then we're getting the tumor type, again, from this data frame, which is a factor, and applying the mean function. And as you can see, we get the means of the tumor volumes at day 20. However, for clarity, we can use the width function like we had seen earlier. So we don't have to repeat the tumor volume day, $, etc. So to call the atomic vector. So in this case, we say day 60 means, for example, where with this data frame, so tumor volume day, t applied day 60, tumor type, mean. And as you can see, if we take a look at the contents, you see that it now has returned again the means for day 60, which are shown here by group. And so what if we wanted to say calculate the number of mice where the tumor volume at day 60 was greater than 300? And well, we could do that as follows with the if-else function. So if-else essentially allows you to pose a question, which in this case is using the boot, or essentially put a logical vector where you have trues and false. In this case, the logical vector is created when we test each element of this atomic vector to see if they're greater or equal than 300. And if so, it will return 1, and if not, it will return false. And so here we go. And now we've also, since we've used this notation here, we've appended the D60 over 300 to our tumor volume day data frame, as we saw earlier. And so if we now take a look, you see this vector or the results have been added to our data frame because we've stored these or appended these results to this data frame. And as you can see, it has ones and zeros. Now, we could say, well, with tumor volume day, which is our data frame, t applied D60 over 300, which is essentially those where it was greater than 300 by tumor type. So let's see. And as you can see, well, for condition A, we had 5 where it came as true, or we returned 1 essentially. And for B, we had none. So this is actually quite useful because, as you can see, it makes posing questions by factor very easy to return the answer. So in this case, it was rapid to quantify the number of mice where we could see larger tumor volumes. And yeah, and it's actually written in much simpler if you can use the width function. And so now let's look at the basics of the table function, which is also very useful. So the table function will work on a vector as well. So essentially we'll take a vector and create a table. So here we're creating a simple vector with these elements, as you can see here, and then we're saying, well, table X. And what you see is it's now kind of taken each element of X and then counted the number of times it appeared, essentially. So 3 appeared twice, 4 appeared 3 times, 8 appeared once, 12 appeared once, 17 appeared once. So you see it's created a nice table summarizing the number of unique elements, summarizing the number of each unique element. And so here we can take our fruits vector and again create a table. So in this case, we have 2 apples, 1 orange, and 1 pear. So this is actually quite useful in summarizing data. So now let's take a look at an experimental example. So let's create a new data frame where we're only taking the first 3 columns, so day 20, day 60, and the tumor type, and storing it in cont. So cont for contingency table. And then, so here you see here, and then let's start asking some interesting questions. So let's say, in this case, using the day 20 data, how many tumors had a greater than 10 volume? And if so, return yes. If not, return no. Okay, and then append these results to the column D20 over 10 in cont. Okay, and then we could do the same thing, but this time ask how many tumors were over 300 at day 60. And again, return yes or no. So you see now we've created this nice little table where, yes or no, whether the conditions were met. And so using the if else statement, essentially where it's true, we put yes, and where it's false, we put no. And so now let's create a contingency table based on the information stored in our two last columns. So here we're taking cont 4, 5, and then transforming it to a table. And then if we look at our contingency table, well, then you can see, here we go, D60 over day 60, where tumor volume was over 300. We have 4 no's, 3 yeses. And then for day 20 over 10 is we have, again, what I meant to say is that we have a nice contingency table where in 4 cases there were no for both at day 10 and day 60, and 2 cases where there were both yes for day 10 and day 60, and etc. So these table functions is actually really useful in creating contingency tables, and you can summarize data and start to look at your data in different ways. Another useful function to apply with the table function is the cut function. And so this is actually very beneficial when you want to bin elements, take elements and put them into bins, which is often the case when you work with numeric values, for example. So let's set the seed so that you can get the same values as me with the rnorm function, which is essentially a random number generator, which will generate random numbers from a normal distribution of mean to standard deviation 3. And here we will create 15 value numbers. So here are 15 numbers, and then let's say we want to bin them according to this sequence. So our bins are between -4 and 12, and so the sequence function will generate numbers between -4 and 12 by 3, so which means -4, -1, 2, 5, 8, and 11. So now we can use the cut function on x and use the bins to help count how many numbers fell in which bin, or how many elements fell in which bin. And so you can see there was only one element that was between -4 and -1. Here you can see it here. And there were 0 elements between 8 and 11. So these are the simplest to interpret, but essentially it summarizes how many elements were found within each bin. So instead of visualizing this as a table, you could also just summarize it as a vector. In which case, here the labels are false. So to summarize this section, we've essentially looked at multiple functions that help you manipulate and work with your data in R, or your data sets in R. So we've learned how to use the subset and width function, the which and grep function, the sort and order function, the sapply and lapply function, and the table and tapply function. In the next video, we'll be looking at how to visualize our data in R. So hi, and welcome to Fundamentals of R Programming. In today's section, section 3, we'll be looking at different methods to visualize data in R. So hence, visualizing data in R. In this section, we're going to take a look at basic plots in R, basic plots with the ggplot2 package, how to visualize heap maps, networks, and look at some other visualization methods implemented in other packages and source code. More specifically, in today's video, we'll be looking at basic plots in R. So in this video, we're going to take a look at built-in plot functions, such as the hist, plot, curve, bar plot, and box plot function. So for these videos, we'll be working with the RStudio instead of R, since I would like you to be able to visualize both the plots and the code as we work through them in the examples. So let us start. So for our first example, we're going to look at how to plot basic curves. And for this, let's first set our working directory. In this case, I'll be setting mine here. And then let's set the seed because we'll be generating some random numbers. So first, for x, let's create a sequence of numbers from 1 to 12 by 1. So as you can see, here we go. And then for y, let's simulate some random numbers from a normal distribution where the mean is 12 and the standard deviation is 10. And so if we look at our values, we have simulated some values for y. Next, let's create a simple scatter plot. And so to do this, we'll use the plot function x, y. And as you can see, the x-axis has our values that we plotted, and then the y-axis has the values that we simulated. So here you can see the basic scatter plot generates these curves. And so now, say we wanted to change the type. So instead of, the basic plot, we wanted to add lines between these dots. And well, we could do that by changing the type parameter. This is quite useful. There's also other settings for type which you can take a look at in the help section. So say we search plot in the help. Well, you can see type has a number of arguments that can be used, namely for points, line, or both. So in our case, B was for both. And you have a lot of other options here. So let's go back to our plot. And say we wanted to now to change the size of those dots and use the color blue instead of black. So here, PSH3 is essentially showing us or using, okay, blooper, please correct that part. So essentially, PSH3 equals 3 allows us to generate little stars instead of those circles that we saw earlier. So as you can see here, I chose the number 3, and as you can see, it was little crosses, and in my plot it generated crosses. But say we wanted to say PCH9, well, it would generate this. If we use PCH20, it would generate this icon here. Or if we generated, for example, a plot with PCH18, then it would use these figures here. So as you can see, by PCH3, we have little crosses. Say we use PCH8, you see it gives us little stars, and say we use PCH23, well, now it gives us these icons instead. So in the previous figure, as I showed you, you can sometimes add a background color. So in this case, the outer shape is blue, but say we wanted to color the inner part of the shape, we could use BG equals red. And as you can see, it now fills those shapes with the color red. So now let's add labels to our plot. And so let's plot XY as follows. Our scatter plot, again, blue, color blue, background red. And then as main title, we'll say plot example video 3.1 as follows. And as you can see, it nicely adds the titles. Now, say we wanted to add labels for the axes. Well, we could use the parameters xlab and ylab as follows. So xlab x values and ylab simulated y values. And as you can see, it has added these labels to our plot. Okay, so now let's move on to histograms. So by default, say we wanted to plot histograms for the simulated values, so y values, we could do. So here you can see it shows frequency. That is because by default, if we look at our help page, that's because default frequency is null. So let's say we say frequency equals true. Well, it gives us the same figure. Now let's say if we say frequency equals false, Well, now you see it gives us density, or otherwise known as probability. So here, we can correct the code as follows. So please edit out this part that I modified. Okay, so now let's add labels and colors to this histogram. So let's do so as follows. So here you can see by using the color parameter, so col equals orange, it is now colored the bars orange. We can change the border color of these with the border argument and say red. So here we've added red borders. And now we can say, well, let's add labels. So labels equals true. As you can see, it now adds how many times. So it had 1, here 2 values that occurred here in this range, 1 value there, 3 values there. And then finally, let's also add a title. So with main, so main equals hist example. And as you can see, we've now added our title. So say we wanted to change the x and y limits of our axis. Well, we could use the y-lim and x-lim parameters. So in the first example, let's set our y limits to from 0 to 5. So here from 0 to 5. As you can see, it looks much nicer. And say now we want to also change our limits for our the x-axis. Well, we could just say x-lim is equal to from 7 to 13. So using a vector to represent these values. And as you can see, we've now modified our histogram. Okay, so now let's move on to the curve function. So to be able to plot an expression or a function of x in R, mathematical function, well, we can use the curve function. And so, for example, we can specify the function that we'd like to plot with the xpr parameter is equal to cos x, and we want to show values from 0 to 8 pi. And as you can see, it plots it. We can also add or use other parameters to add, for example, a title and color to our plot. So here we've added the title f of x is equal to cos x, and now we have our lines colored purple. Another useful trick is, say we wanted to increase the width of the line, so we could use the LWD and set it to 3 instead. And as you can see, it generated a thicker line. So now let's look at a practical example working with data frames. So again, let's set the seed so we can get different random numbers, and we'll simulate the height of 12 individuals using our norm, and then with the mean of the distribution being 150 and standard deviation of 10. And then we'll group them into either A or B as follows by sampling from the vector A and B 12 times, and we say replace equals true so that it can always pick back from A or B. So let's take a look at the values we simulated. Here we go, and then look at the groups that we simulated again, so BB, AA, etc. And now let's create a bar plot. So here I'm going to again change the seed because I want to simulate again colors from the colors palette available in R. And to do that, I say sample colors. I say distinct equals true here because I don't want to use shades of colors. I want to make sure that the colors are considered distinct, and I want to sample 12 colors. Okay, and I've stored these in my palette. So if you take a look at my palette, you'll see that it's simulated or sampled 12 colors from the colors available. And if you're curious about the colors function, well, you can take a look again in the help section. And as you can see, this gives you a lot more description on how the colors function works and how to generate palettes using it. Okay, let's go back. And so now let's create a bar plot. So we could do that using the bar plot function. And so here we're saying, well, bar plot height, and use the colors my palette, and name.arg equals group. So I want to use the groups that I've simulated. And as you can see, B, B, A, B, B, etc. So it looks pretty nice. Now, say we wanted to visualize these labels vertically instead of horizontally. Well, we could use the last parameter, LAS parameter, equals 2. And as you can see, now the labels are vertical instead of horizontal. So just a brief explanation. So why we use LAS is equal to 2. Well, it essentially is one of the graphical parameters. And as you can see, 2 says always perpendicular to the axis, which is essentially putting the labels vertically. If we use 1, always horizontal, and if we use 3, always vertical. So very useful tool. Again, here, all you need to do is search for par, and you will have more details on the parameters for graphics in R. Okay, so now in this last bar plot example, we can add, for example, define our y-axis with ylab and specify height in centimeters. So as you can see, we've generated a nice bar plot here. So now let's go on to creating box plots. So now I'm going to create a data frame, as I mentioned earlier. Okay, so now let's move on to our next example, which is to create a box plot. So for this, let's create a data frame of our height and group as follows. So if we take a look at df, as you can see, it has height and group as a second column. So now we can use the box plot function to plot the height by group and color each box a different color. So here, essentially what this means, the symbol here, is that it's height a function of group. So otherwise, you could read it as y and a function of x. Okay, so this is a very useful symbol, and generally this here is a factor. So here I say I can just directly use height and group. I mean, we could have because there exists as objects in our environment, but also because we can specify which data frame to use with the data argument, and then we choose the colors. So if we plot that, as you can see, well, the mean here, the box plot shows the median height in group A, and then the median height in group B. Okay, so that's pretty much some of the basic plotting functions in R. And now a useful tool is how to save images. So to save images, you can do so as follows. So you would use PNG function here, where let's just copy it first. You see that we've specified the file name, the dimensions, so the width, the height, and the units, so it's in inches, and the resolution, which in this case I use 300. And the next line of code you need to enter is your actual plot. So in this case, it's our bar plot that we generated earlier. Okay, so you won't see anything appear on the screen. And then for your, because it's being automatically saved as an image, and then to be able to successfully save your image, you must remember to put graphics.off, or to use the graphics.off function. And so now, if you go into your working directory, so in this case, I could do that just by listing files to show you. You'll see that, well, I already had the image stored, but here you see bar plot example 3.1.png, and if you open it up, you'll see your image. So this is great. So as a second example, how about we just plot up our box plot to a PNG file as follows. And then don't forget to include graphics off, and you've just saved your PNG file. And if we open it up, you can nicely see that it's saved the file successfully. So this is quite useful. But we've learned how to plot basic figures in R using the plot function, bar plot, box plot, etc., and how to save these images. In the next video, we'll be looking at how to generate some basic plots with the ggplot2 package. So thank you very much, and I'll see you in the next video. Hi, and welcome to Fundamentals of R Programming. In today's video, we'll be looking at basic plots with the ggplot2 package. More specifically, we'll be taking a look at how to generate histograms and scatter plots with the ggplot2 package, how to add labels and use the ggRepel package to visualize these labels more appropriately or more aesthetically, and how to use the code that we've learned to generate a volcano plot using this package. Again, for this video, we'll be using RStudio so that you'll be able to take a look at the plots as they're being generated. Okay, so the first thing we're going to do is we're going to set our working directory and load the necessary package. So in this case, Biomart. So in this case, Biomart, so we can simulate gene expression data. So here, you could run this code. It's just to essentially generate a list of gene symbols from the human genome. And then now we're going to select 50 genes at random. So let's set the seed first. And then get these genes. So if we take a look at the first 6 genes, you can see we've simulated these values, these genes here. Okay, and now let's simulate some gene expression values. So in this case, we're going to use the R or runif, or essentially runif, so to generate random numbers from a uniform distribution where the minimum value is 0 and the maximum value is 20. And then we're going to store it in the express value vector, and then we're going to name the elements in this vector according to the genes object we created earlier. So if we inspect this object, you'll see here you go. We've now attributed these values to the genes mentioned above. Okay, so now let's load the ggplot2 package and plot some histograms. So the simplest way to generate a histogram using the ggplot2 package is to use the qplot function. So it's kind of like the most basic function available in R. It's quite similar. So here we're just saying qplot, our vector here, and then we're using the geom argument to specify that we want it plotted as a histogram. Okay, so you can ignore the warnings that you're getting. Essentially, it's just telling you that, it would probably be better to specify the bin width. Okay, so here you can see it's generated a plot as follows. Now, say we wanted to spice up our plot a bit. So in this case, what I mean by this is add bin width. So here we're going to use a bin width of 5. Then we're going to add a title using the main argument. So simulated expression values, xlab to change the label here. And then we want to actually color these bars in green. So fill them in with green and color the outer with red. And then alpha just specifies the transparency. So we want a transparency of 0.4. And it's very important that you use the I function in this case, because the I function is mostly used here in this context to nest the color. So if you want to avoid error messages, don't forget your I functions. But you see, it's nicely generated our histogram with bins of 5, and it's colored according to our specifications. So now, this is using qplot. Most people who work with the ggplot2 package don't actually use qplot, they'll use ggplot directly. And so let's do that. And to do so, let's first transform our vector as a data frame using the as.dataframe function. Let's take a look by looking at the head. And you can see it looks very nice. And then we'll do ggplot. So this is a bit different from what you're used to seeing in the sense that you have your function and then we're adding on other functions to this function with the plus here. So here we're saying ggplot. Data is our data frame, so equal to our data frame. Our aesthetic, so AES parameter is that we want to plot x is equal to express values. And then we're specifying that we want it plotted as a histogram with the gm_histogram function here. Okay, so again, it's telling us we should pick some bin widths, but you generated the same plot as earlier. Alternatively, it might be simpler to, and what's neat about ggplot is that you can store your image into an object and then you can add on to that image using the additional function. So for example, we could have just said the first part, so ggplot data is equal to df and then specify which aesthetics to plot, so our x equals to express values, and then stored it into pp. So our object, we're calling it pp. So as you can see, it hasn't plotted anything new. In fact, to be able to plot the image, we would have to, if we just run pp, it would, you can see it's just the very basics, right? Now we need to say, well, we can add the gm histogram function to specify that we want our image plotted as a histogram as follows, and as you can see, it has now regenerated the same image. So sometimes it's easier to work like this because, you know, you can start off with one idea in mind, and you can just, instead of starting from scratch or rewriting the full code, you can just start with pp and then plus, you know, what you're interested in. So in this case, let's add again the gm histogram function, but now let's specify some of the parameters. So here we're saying we want bin width equals to 5, the color we want red, the fill green, and alpha 0.4. So, and here you notice that you no longer have to use the I function. So you can just specify your colors directly, and as you can see, it generated the plot we generated earlier. Otherwise, you can again store it into an image, right? Object, so pp2, and then to be able to visualize pp2, so let's just do pp1 so that we can clear the screen. pp2, and you can see all we have to do is specify the object and it will then print your image. We can add more details to pp2 as follows. So again, instead of rewriting the first part of our code, we'll just say pp. So as you can see now, we could add titles to our plot as follows. So again, we can just call up pp2 plus and then use labs function title simulated expression value labs x plus labs x equals values as follows. And as you can see, we've now specified simulated expression values as our title and change our x label to values. So say we wanted to add a density curve to our histogram. Well, in ggplot that's actually quite simple. So let's go back to our first plot that we generated with pp. And then here we're going to use gm_histogram. Here we're going to specify aesthetics y is equal to ... density ... So that's what you need to enter in order to specify density. Then we're going to have the color be blue, fill green, alpha 4 or 0.4, and then we're going to use the geom density function to specify the density parameter and specify the size or the thickness of the line with 2. So as you can see, it's generated a nice figure here. We could, instead of using PP, we could use our second plot that we generated, so PP2. And okay, so please edit out the part where I show this example here. Okay. Okay, please edit it out. Okay. Okay, and please edit out my cat's meow. Okay. So now for the next series of examples, let's simulate some expression values for those 50 genes in what we'll say is our knockout animal. So stored in this here, this object here, so expression values, and KO is essentially taking our expression values vector and adding random numbers. So 50 random numbers from 1 to 4. There we go. And then let's add our gene names. And then let's create a data frame here called df2, where we'll say wild type is equal to the express values, and knockout is equal to express values KO, or knockout. And print the first 6 lines of our data frame, and as you can see, we have got the data here. And now let's use ggplot to create a scatter plot. So now let's create a scatter plot using the data stored in df2 as follows. So here we'll just specify ggplot df2, and then here we're going to use geom_point for our scatter plot, and then we're going to plot wild type and knockout. The color is blue, and then we'll use geom_text to actually add the name of the genes as follows. So as you can see, it's now created each point with geom_point and or geom_point, and then it's added the names with the geom_text function as follows. So as you can see, the labels are very hard to read because they're one on top of another. So a useful package to have is the ggRepel package. So let's load it up. And now rerun our code as earlier. Okay, and now as you can see, instead of using geom_text, we can now use the function geom_text_repel, and again with the same parameters, so our aesthetics, wild type, knockout, our data, remember, is specified in ggplot up here as df2, and then we are going to use the labels, so the row names of df2, which contain the gene names, as our labels. And here you can see it's nicely separated the labels so we can see them. So say you don't like the gray background, where it's quite easy to change that with ggplot2, in that we can just use the theme_bw for the white theme, base_size equals 16. As you can see, the other part of our code remains the same, but now the background is white. Or more specifically, our theme is base_size 16. So now let's just finish with a practical example. So for this, we're going to create volcano plot. So volcano plot essentially shows you fold change and also p-values. And it allows you to kind of highlight genes that are important or differentially expressed between your two conditions. And it's a very useful and visual way to see or look at gene expression data. So for this example, let's just load the R object directly as follows. Okay, and if you take a look at what we just uploaded, we can say head. As you can see, it's essentially a couple of the genes here, the log fold change, the average or base mean, t-value, the p-value, the adjusted p-value, and the b-statistic. And so, first thing we're going to do is we're going to create a column called significant, where all the genes that have a p-value, so in the p.value column, less than 0.001, well, we'll say p less than 0.001, or else we'll say not significant. And to do this, we'll use the if-else function. So to see what this actually looks like, we can take a look at the results here. And as you can see, we just created or appended this column to our existing data frame using the $sign. But here I just want to show the atomic vector, and as you can see, the first genes are not significant. Okay. And then we'll just have another column called gene, where we'll store the row names, which are essentially the gene symbols. And so now if we take a look, here you can see we've added these two columns to our data frame. And so now let's plot our volcano plot. So here's the code. So let's just load it all up and I'll go through it. So here the first part is ggplot. The data frame is exlfc data. We've specified our aesthetics to plot. So on the x-axis we'll plot the log fold change, and the y-axis will be minus log 10 of the p-value. Then we'll use geom_point to make sure we get a scatter plot. We'll use scale_color_manual for values. So gray if they're not significant, red if they're significant. Theme _bw base_size equals 16, so we can get it white. And then we'll use geom_text_repel to add the labels to all the points that were significant, where the p-value was less than 0.001, as follows. And as you can see, we've got a nice volcano plot here. So as you can see, most of the genes were not significant because they're all gray, but those with a p-value less than 0.001 are highlighted in red, and also the label or the gene names are added as well. And the gene names don't overlap because we've used the ggRepel package, geom_text_repel. So this is actually a really great tool to be able to use when plotting scatter plots or other plots that are useful in biology, such as a volcano plot. So in summary, we've used the ggplot2 package to be able to plot basic plots such as histograms or scatter plots, and even use ggplot to create a volcano plot. And now in the next video, we'll be looking at how to visualize heat maps, so visualizing heat maps. So thank you for watching, and see you in the next video. Hi, and welcome to Fundamentals of R Programming. In today's video, we'll be looking at how to visualize or generate heat maps in R. In this video, we're going to take a look at the basic heat map function, the heatmap.to function that is implemented in the gplots package, and the heatmap function that is part of the complex heatmap package. So just to recap, the file that I'm using is the code file available on the website, and I'll be running the code in RStudio so you can see the plots more easily. Okay, so here, just setting my working directory. Okay, so now let's load the expression data that we'd like to plot. So that we'll be using for our heat maps. And this is also available on the website. Now let's transform this data frame into a matrix with the asMatrix function, and then look at the contents of our object that we just created as follows. And as you can see, there are genes and then samples. So now we're going to use the heatmap function that is actually part of the base package of R, so the stats package. And so if we just do heatmap with our mat1 object, this is what we obtain. So you see we've got our genes. It's here it shows the heat map and the clustering. So to have an idea of what the default parameters are for the heat map function, it's important to look this up in the help. So if you're just using the console, then you would do help heat map, right, as follows. And as you can see, you have access to the help page where it specifies what all the default parameters are. So as you'll see, the distance by default, if we look at the distance function by default can be obtained by clicking here, which by default is the Euclidean method that's used. And then if we look at the default agglomeration function, or hclust function, we can click here and you see it defaults to complete. So bearing that in mind, there are multiple parameters you can change to modify your plot. So for example, say we don't like this color scheme. Well, we can use the cm.colors palette as follows. And as you can see, it's now implemented this color change. We can also scale our data, so scale the visualization, because as is, the heat map is just plotting the values in mat1, in our mat1 object. But say we wanted to scale by row, which makes it easier to cross-compare. We can use the scale and then specify row. And as you can see, well, by default, it seems to be scaling by row if we compare the two. So let's see. This is default, and then this is scale by row, and you see nothing changed. So by default, it scales by row. And let's see what happens when we scale by column. As you can see now, the values are scaled by column here. So we can customize, like I mentioned, some of the functions used to generate the heat map. So in this case, we're going to use our own function for the distance measure and say change the default method to the war d2 method for the hclust function. And so to do this, we're creating two functions. The first one is, I'm calling it coordist, but it's essentially just the similarity, so 1 minus the correlation, as follows. And it's important that it is a function because that's what the argument takes. And then here we're creating a new hclust function here defined as hclustx method equals war d2. Okay, so now that we've stored that into our session, now we can say, well, rerun the code, but this time specifying that our hclust function is hclust.avl that we just generated, and our distant function is coordist. And as you can see, it now clusters our data according to these functions. So there are also interesting features that you can also modify with the heat map function. Namely, the heat map function also allows you to specify, for example, your group colors or other parameters that might be of interest that might make your visualization or your interpretation of the interpretation of the data simpler or better. So, for example, call side colors are often used in heat maps to determine groups so that we can see how these cluster. And so let's define our groups. So we'll have two groups, A and B, because A1, A2, and A3 are part of the same group, and B1 and B2 is part of a separate group. And so you can see this as follows. Okay, so for the call side colors argument, you need to make sure that this is a factor. So we are saying as factor, and then we need to choose the color palette that we want to work with for our groups. And so in this case, we're using navy and purple. So now in our function, you'll see that we now specify the call side colors argument as equal to pal group. And what this means here is that essentially it is telling the program exactly which color to use for which sample. So one thing that you need to make sure of is that the order in which you specify your groups has to match the order of the samples in your matrix. So for example, if we look back at our matrix, you'll see that we had A1, A2, A3, B1, B2, and so A, B, B, and the colors will also match navy, 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 purple, purple. So you need to make sure that the groups that you define using the factor function match the column names as is in your matrix, or else it will not assign the appropriate color to the right sample. Okay, so now, for example, What if you didn't want to cluster your heat map and just plot the matrix values, or you only want to specify clustering for the rows and not necessarily the columns? And so you could do this again in the heat map function by specifying call v equals NA. And so call v equals NA just means that you're not going to apply clustering to the columns. And so when you do this, you see that now we only clustered the rows but not the columns. And just to contrast, if we go back to the previous line of code where here we define our call side colors and we apply clustering, this is what the data looks like, or the heat map looks like. I would say that the heatmap.to function is more applied because it also allows you to modify more parameters, and you can actually get, for example, a legend for your color scheme, etc. And so to do this, we will need to load the gplots package as follows. So we will need to load the gplots package as follows. Okay, and now we will use the exact same code as above, except that now we're using the heatmap.to package. And so let's see what happens. And so as you can see, the advantage of the heatmap.to function over the heatmap function is that you can visualize the color key and used here. And so here this is just with the default settings with trace equals true, and so now you have a trace. But we can remove that by specifying trace equals none. And now we have a similar heat map as before, but this time with the color key. Another advantage of the heatmap.to function is that you can use predefined color palettes that are actually quite popular when you look at papers, etc., like the red-blue palette. So this is implemented in the gplots package, and so when we run the code, well, now you see we have red and blue instead of our CM colors. One of the things that you'll notice is that now it's coloring red as -1 and blue for +1. So this is kind of counterintuitive. So what we need to do is change the color scheme by using the rev function, which is essentially just the reverse. Okay, so it just specifies to reverse the color scheme. And as you can see, now you have a more conservative view where the blue is the negative and the red is positive. You can also use other color schemes that are implemented in the heatmap.to function or gplots package. For example, we could use the red-green function, and again we have to use reverse or rev, so we get green for negative values and red for positive values. And now you've just created a heat map for gene expression values. So the next thing you're going to want to know sometimes is, well, I'd like to save my heat map in matrix format. So essentially I want my matrix to be represented as it's shown on the heat map. And so to do that, you can store the results from the heatmap.to function. Oops. As follows into our object we call HM. And then if you look at HM, the names, because it's actually a list, so you can see the names. So you have multiple elements in this list, so row in, call in, etc. And as you can see, well, if we look at row in, you see that it specifies the ordering of the rows, and here I'm just plotting the first 6 values. And so say we wanted to create a matrix, actually align our matrix in the exact same way as we see the heat map, well, we would do so as follows. So here, when we look at it now, so here we just say we need to use the reverse of the row end, so HM $ row end, and keep the HM $ call in, which essentially means to take the vector here. It's the $ is specifying atomic vector. And when you do that, well, you see, here we go, B1, A2, B2, A1, A3, and then you have your first 6 genes match the first 6 genes here because I'm only printing the first 6 lines with the head function. And so the last heat map function I would like to go over is the complex heat map function, and I actually think it's very useful because unlike the heatmap.to function where you can only specify one group or grouping or call site colors, with the heat map function you can actually do a lot more. And so you can have multiple groups, you can do a lot of things. And so just as an introduction to this package, we will load it up and create a heat map. Okay, so and the heat map by default created the heat map function is as follows. And so you'll see it has clustered, but also that it's actually plotting the values as is across the samples, and there is no scaling by row, etc. So say we wanted to change the first thing we want to do is change the legend annotation. So we could do that using the parameter heatmap underscore legend param underscore param as follows, and now you see it removes it. Next, say we want to actually specify the clustering methods used. Well, in this case, we can say clustering distance of the rows should be Spearman, and say the clustering method for the rows should be Ward B2. And so now it's gone and implemented that. And what's interesting about this function is that you can specify different clustering methods for your rows and columns separately. So now I've just done the rows with Spearman, and say in this next example, I'll cluster the columns by Pearson correlation, and then complete instead. And so here you go. And so you can actually combine both, which I'm not going to do now, but you can actually combine specify, for example, a different method for clustering rows and columns together quite easily. So if we were, say, to do that, it would be, we could just copy paste this part of the code, add it here, and then enter it. And so now what you see is that it's used the Spearman correlation for the rows and the Pearson correlation for the columns. Okay, but more importantly is one of the unfortunate aspects of this function is it doesn't have a simple scale argument to scale your rows. And so to do that, you need to first scale your matrix before using the heatmap function. So to do that, here we use the t, so t function, then we scale the t of the matrix 1, and essentially that converts it to a scaled matrix. So the t function just means transpose. And then we can now plot this this scaled matrix as follows. And you see that it actually looks like what we had plotted earlier with the heatmap.to function and also the heatmap function. And so other interesting things you can do with the complex heatmap function is that you can load additional libraries such as the circlize library, where you can then specify your color scheme with the colorram2 function. And so for example, here I'm just saying, well, I want to go from green 4, this part here is just is the hex code for the color gray, and then I can even specify the space. So here I'm using the LAB space, okay, and then I can replot my heat map, and as you will see, it's now used that color scheme and the space I asked it to use. Instead of the LAB space, we could potentially use the sRGB space. And so to do that, we just need to change the argument in F2, right, just here, and then again, replot our heat map. And as you can see, the actual color space makes a difference on the intensity of the green or the color that you're seeing. So these are interesting parameters that you can tweak to get beautiful heat maps. Finally, you can use the heatmap.to function to actually do the clustering, so you can actually have a quick visualization and then just directly use those dendrograms produced by that function in your heatmap function. And so, for example, earlier we saved, remember, if we go back, we looked at the names HM, right? So here we actually have a call dendrogram and a row dendrogram list object. And so here we can say, well, let's cluster our columns using the HM call dendrograms element. And as you can see, here we don't even have to specify what clustering methods to use. You can just directly use the clustering methods that you ran using the heatmap.to function. And this is actually very useful, for example, because it's very quick to use heatmap.to, and then if you want to do a more extensive heat map, well, then you can move into complex heat map. And then finally, one of the advantages is that you can add multiple annotations or call side colors. And so for this example, we're just going to first create our heat map annotation object, which essentially, and I won't go into too much details, but I will recommend that you check out their vignette for the bioconductor page, because there's a lot of good tutorials. But essentially, we've created our heat map annotation here, and then we can specify in our heat map function to top annotation equals HA. And so what this means is that what we've specified here now, well, it's our call side colors that we essentially specified using the heat map annotation here. But what's good is about this function is that you can actually add additional groups and factors in. Okay, and say you wanted to, again, you weren't really interested in clustering the columns, well, you could quickly specify cluster underscore columns equals false. And that's exactly what it does. Finally, you can modify your dendrogram attributes. You can use the dend extend library in combination with the complex heat map package. And so here I'm just storing my dendrogram into a dend object, and then I'm saying, and then for more information on the nomenclature used in the dend extend package, again I recommend that you check out the HTML vignette that accompanies the package. And here all I'm saying is, well, color branches k equals 2, so it's going to split my dendrogram into 2 and color accordingly. And as you can see, it has separated my dendrogram based on the height that gives 2 clusters and colored the dendrogram accordingly. And so we can actually play with some of the parameters. For example, we can increase the branch size as follows. And again, visualize the heat map. And as you can see, using some of the features that are part of the code conventions that you can learn using the dend extend package, you can actually implement it in your complex heat map. And so for more information, I definitely recommend, for the complex heat map at least, that you check out the bioconductor webpage, which is available at the bottom of the code. To conclude, in this video we learned how to visualize heat maps using the gplots package, the complex heat map package, and also the base stats heat map function. And in the next video, we'll be visualizing networks. So thanks for watching, and see you in the next video. So hi, and welcome to Fundamentals of R Programming. In today's video, we'll be learning how to visualize networks in R. So visualizing networks. In this video, we're going to take a look at how to create basic networks with the iGraph package and visualize protein-protein interaction networks from gene lists. And now let's create a basic network. So to do this, we're first going to create a network without any edges. And to do this, we will need to use the graph.empty function. And essentially n equals 12 means that we have 12 nodes and it is not directed. And this is stored in the object G. And if you look at G, it's essentially an iGraph object. And so to plot this, we need to use the plot function. As you can see, it has created a network with 12 nodes without any edges. Now, to create a complete network without any self-edges, we can use the graph.full function as follows. And then, as before, we do plot G, and now we actually have a network with edges where everything is connected to everything else. So to plot the nodes as a ring, for example, we could use the graph.ring function as follows. And again, we will need to plot this object with the plot function. And so now you see 1 is connected to 2 and 12, 2 is connected to 1 and 3, etc. You can also have your nodes arranged as a star as follows, using the graph.star, and there are two options where there is mode out, which you can visualize as follows. So 1 is connected to every other node, and now everything is connected to 1. And so to, for example, create a network where you have defined edges, for example, we can store our edges in an object we call edges. And so this is 1 to 2, 3 to 2, 2 to 4, 5 to 1. And then we say graph edges and max equals edges. Directed is true. So we want to consider the direction, and then we can just plot as follows. So it's exactly what we specified. So 1 to 2, 3 to 2, 2 to 4, 5 to 1. And since it's directed, the first number goes to the second one. Alternatively, you could have first created an empty graph object and then added the edges using the add.edges function. And again, we can plot as follows. And even if it's not exactly arranged the same way, the network is built the same way. So say we wanted to change the names of our nodes and give them gene names, for example. Well, we need to use V, and I think V stands for vertices, but I have to double check, so don't quote me on that. But essentially, here for each one of our nodes, we are defining a gene name, and then we'd like to color these nodes gray, except for, say, LRRC19. And so to specify this, we will use the VG, then with the brackets, almost like you would use index positions or a vector for that matter. Here you're saying name equals LRC19. And here we're specifying color red. And so now we can plot our network. And if you take a look at the iGraph package, you'll realize there are multiple layouts you can choose from, and you can even see this with the help function for the iGraph package. And you'll see now we're using layout.circle, so we're using a different layout. And here we're coloring the vertex.color
using what we specified here, and we're using the label, so vertex.label, with what we had defined here. And the vertex size, so 30. And as you can see, it's done just that. So again, we first had numbers here to show directions or directionality, and then now we've color-coded our nodes and specifically highlighted the node of our gene of interest. So to learn more about the plot function, you can actually look at the help page, which will be under plot.igraph. And you'll see there's a lot more options that you can use to create your network. And so now the next part of the video will be to focus on protein-protein interaction networks, and more specifically how to visualize your PPI networks in R from a gene list. And so here I'm just going to, you can read the file that's available on the web page. Then we can take a look at what we've just loaded. And so what you see here is the interactions. So map K8 interacts with map 2 K4, etc. And these values were actually taken from the stringdb.org database when you search for map K interactions in human. And so here I just saved the, how many, let's check the dimensions. Yeah, I just essentially took the 215 interactions and stored it. But essentially you could do the same thing. You could look for your protein of interest on stringdb.org and actually visualize these networks or interactions in R with iGraph. And so again, if you haven't done so already, you would load the library, iGraph, and here there's a nice function that says graph.dataframe, graph.data.frame, which essentially allows you to graph your PPI data frame that we just loaded. And then now we need to specify, again, the plot function, but here I'm going to change a couple of parameters before visualizing. So for example, this time I'm using the layout.fruchterman Rheingold. I'm using the labels VGG name, and then I'm specifying the color should be black, edge arrow size, and edge.curve equals false. And essentially what this does is, as you'll see, it allows me to specify that I want to include the names of the genes. And if you look back at the head object, it will essentially take the name of the gene. Black just means that here it specified the color is black and the size, the edge arrow size is as small as possible. And edge.curved is false, because if we had kept it as true, we would have the following. And so I personally prefer straight lines, but if you like the curved visualization, you can use that too. So if we go back to false, there we go. And so it's very important to remember with networks, like they might not always be arranged the exact same way. You're actually using a layout to try and optimize the distances between your different nodes. But that's something you can always play with in R. So there are other packages that you can also use to visualize networks. In this case, we will use the graph and R graph viz libraries. And to do that, we'll actually take advantage of a piece of code that I found on this following website here, where it allows you to make your protein graph. And so here I'm just going to load the function into our session. Then I'm going to load the two libraries
And now we're ready to plot our PPI. So here now we just need to use the function that we've just defined. So make protein graph PPI. And then we're saving it into the PPI graph object as follows. And then now we can choose the layout graph. In this case, we'll choose Nito. And then to actually visualize the graph, we'll need to do render graph, use the render graph function. And as you can see, it is now generated again our network. And so it's different. They both allow you to create networks. It's up to you to really choose what you want to use. I think iGraph is a bit more popular with people who work on networks in R. And then there are those who prefer to use other tools like Statistical. But at least in R, you can at least play and create your own small networks or even create networks from scratch. So this is a really great tool to use, even if most people will use, for example, Statistical. In summary, we learned how to create networks, and we did this using the iGraph package and also the graph and rgraphiz package. And we also took advantage of creating protein-protein interaction networks using information stored in databases. And so just for you to follow up on, if you're interested, you can always go to the stringdb.org database. You can type in your gene of interest, which is what I did here, mapk, and then save the network. So here's the network as visualized on their web tool. And essentially this network you can save as an SVA, as a text file or as a CSV file. And this file you can then load as a data frame and create a network in R as we just did. And so in the next video, we'll be looking at other visualization methods that might be useful when plotting your data. More specifically, when trying to replicate some of the graphs that you're used to seeing or box plots, etc. that you're used to seeing in Prism, you can actually generate some of these using other packages. So hi, and welcome to Fundamentals of R Programming. In today's video, we'll be looking at other visualization methods in R. More specifically, we're going to take a look at how to create box plots with ggplot2, but also how to create box plots a little bit more reminiscent of what we would generate with Prism and other tools that you're most likely to see when you read papers and often use in bioinformatics, such as those that we can create with the easy ggplot2 package. So this is a great tool to be able to generate box plots that give other information where you can actually see your samples. And finally, we'll look at some other plots that you can generate with easy ggplot2 that might be very meaningful for your research or to display your data. And so easy ggplot2, just to give you an introduction, you can get a lot more information off of the wiki page, but it's a great way to actually generate box plots and other related plots where you can actually see the distribution or the actual value for each individual sample, and instead of just summarizing it as just a box plot. So first let's set the working directory, and now let's first create a box plot with ggplot2. So let's load the data. So this data again is available online, and essentially when you load tumor volume _2_5.rda, which is essentially that file that we had used in video 2.5, we get a summary for measurements taken on day 20 and day 60, in fact the tumor volume measurements, and the third column has the tumor type. And so the first thing you need to know with ggplot2 is that you cannot just use your data frame as is, so you need to first transform that data frame with the reshape2 package. And so to do this, we're essentially going to use the melt function to create the format needed to use for ggplot. So here we go. So essentially we use the melt function, and then we need to specify what are our variables. And so in this case, our variables are day 20 and day 60, which are the two first columns here. Now if we take a look at the head of the object that we just created, well, you'll see now this is, it tells you tumor type, A, B, etc., and then it gives you each variable. So here we're just showing day 20, but if you look at the full object, you'll see day 60 as well, and the value. And this is the format that we need to actually use the function. So first thing we're going to do is store our ggplot into object pp2. And here you see we're specifying the x-axis should be the tumor type, and the y-axis should display the value. Okay, so once we've loaded our library, now we can actually generate our plot of interest and say stored in pp2. And then now we need to specify that we want it as a box plot using gm_boxplot. And as you can see, it now nicely generates a box plot of, for the values in A and B. So say now we wanted to color code, or at least fill each box plot by a variable, which is essentially day 20 and day 60. Well, then in this case, you nicely see it now separates day 20 from day 60 for A and B. And now say we wanted to adjust the scale. Well, we could do that as follows, or by adding scale _y_log 10. And now you can see we've just generated a really great box plot. So now let's see how to generate box plots with the Easy ggplot2 package. So to install, you'll need to follow the instructions to be able to install packages from GitHub. But essentially, once you have that installed, you can load the package and we can generate box plots with centered dots, which is actually a nice way of visualizing your data. And so to do this, we need to use the ggplot2.2 box plot function, and then we specify the data, which is taken from this data frame, and X name is the tumor type and Y name is day 20. And then we ask to add dots, we specify the dot size and dot position. So here it's going to tell you to pick different bins. We don't need to worry about that, but essentially what you get is you can actually see the distribution of the individual points in your box plot, which is pretty neat. And you'll notice that we didn't necessarily have to reshape or create or use the melt function to create an object to run with the ggplot2.boxplot package. So it's great because it means you can just work from the data frame directly. And here in our next example, all I did was add or some of the arguments, such as add the main title, the X title, the Y title, and change the background color. So it's pretty great. Say you wanted to just get instead of the box plot and the dot plots, you just wanted dot plots. Well, you could do that with the ggplot2.dotplot function as follows. And here you can see the individual points without the box plot. And maybe you might be interested in a different visualization method, such as like the violin plot. And so to do this, we could just use the ggplot2.violin plot, and you get your plot as follows. And here you just see that we specified in this tape group colors because we wanted red and navy. Show legend is false, so I'm not showing the legend here. And then most of the parameters are true or the same as before, except now we're saying add dot is equal to true, and we're specifying the dot size. So I definitely recommend that you check out the web page here to get some more tips and how to use the function or different functions available in the Easy ggplot2 package. So as I mentioned, one of the advantages is that unlike with the ggplot2 package where you need to reshape your data frame with the melt function, in the latter you can just use your data frame as is. One of the advantages, however, is that you could generate the figures that we had generated earlier, where we can actually split by variable here, which is very interesting. So I guess it really depends on what your needs are, but in either case, both packages are very useful for generating these types of plots instead of using some of the commercial tools like Prism. So in summary, in this video we saw how to use the ggplot2 package to generate box plots, the importance of using the reshape package to generate an object or data frame that works with the ggplot2 box plot function. We also learned that we could just use the easy ggplot2 package to work with our data frames as is and potentially have really nice graphical features such as adding points, for example, for the individual cases, or change from box plot to dot plot or violin plot, strip chart, and there's a lot more methods that you could potentially use in the easy ggplot2 package. So in summary, in this section we learned how to create basic plots with R, we learned how to create basic plots with the ggplot2 package, we learned how to visualize heat maps and networks using different R packages, and finally we learned how to use other visualization methods such as those implemented in the ggplot2 package. And so in the next section we'll be looking at flow control and debugging tools. So thank you for watching and see you in the next section. Blooper, thank you for watching and see you in the next section. Okay, thank you. So hi, and welcome to Fundamentals of R Programming. In today's section, we'll be looking at flow control and debugging tools. More specifically, in this section, we're going to take a look at the for loop and how it contrasts or how it compares to the apply function that we've seen earlier. We will also look at the if statement and if-else function to see how to use these and work with them in our code. We will also learn the while repeat loop and the break statement and how to use these together. And then we will see how to write our own functions, and we will end the section with learning some general programming and debugging tools to help get your code working. Okay, so in today's video we'll be looking at the for loop and compare it to the apply function. More specifically, in this video we're going to take a look at how to write for loops, how to time our code, so we can look at the efficiency of the apply function versus for loops. Okay, so you can download the code, and the first thing we're going to do is write a very simple for statement. So here we're just using the example code for 4.1. And so in this statement, what you need to do is you need to write out for, and then we need to say I, but you can use any variable. It could be A, B, C, D, E, F, G, etc. Conventionally we use I, but you could use another letter in 1 to 12. And what that means is that every time it repeats the loop, I will go from value 1, 2, 3, 4, etc. until 12. And then it will and then only then will the for loop be ended. Then we can add some brackets here. And then we can just say something simple like print I. So this time when it runs the for loop, it will actually print the variable I. And as you can see, it prints 1, 2, 3, etc. until 12. We could have also written our for loop as follows. So for very simple for loops. For more complicated ones, I think you would need to include the brackets. For I in 1 to 12, print I. Okay? And you see it works the same way.
So for really simple statements that you can all fit in one line, you could get away with this notation. Okay, let's look at another example where this time we are again going to say for I in 1 to 12 and open brackets y I plus 10, okay, and then so if we just do that, you see nothing prints to the screen. However, if we use this notation, so please, you'll have to use the text editor because it's not as easy. It's not as easy, but it's clearer and more legible to use a text editor and then copy paste in this case. Okay, and here you see that now it's actually printed those values. So really, the for loop is almost like a function in that whatever equations or whatever a process is done within the for loop, it does not necessarily print to the screen. So if you want to visualize the contents, then you have to use the print function. So now let's look at a practical example where we have a list of genes taken here. So these are a bunch of mouse genes, and we would like to create or a new gene names by modifying these. And so to do this, we're going to take advantage of the for loop. So the first thing we need to do is that we need to define a variable where we actually store the modified version of the gene. So before writing your for loop, let's create a new gene names object that's an empty vector. Okay? So that when we run our for loop now, it will be able to store the contents in this vector. And so essentially all this means here is that we're taking I and we're using the paste function to add 1 to I, and it's separated by dash. And then to be able to store this, we say, well, in our new gene names object, add new gene names, which is in the beginning it has nothing, but as the for loop runs, it will accumulate. And then add this new row name. Okay, so it's very important to do this because even if at first your vector is empty, you want to be able to store the values after each iteration. And here we go. So now we print new gene names, and as you can see, it has added 1-1 to every gene. So this is really important because if you do not, for example, if you just thought that, oh, I'll just save it in new gene names directly, well, what you would have realized is that it's just going to store the last value. And that is because the variables are changed each time, like you input a new variable each time you ran the for loop and not necessarily stored it. There's other ways you could have written this for loop, and I'll leave it up to you for homework to figure that out. So, and I'll give you a quick hint. You could have created a vector that has 6 elements and then added each gene name to a different index position. Okay, so we've printed the contents, and now let's try and make the gene names unique. So we could do that by saying, for example, here. So now for our next example, let's make the genes unique by adding values 1 to 5. And so to do that, we'll take advantage of the sec function, which is essentially almost like it's the same thing as writing 1 to 5. So, and we could print the contents here, and you'll see it's 1 to 5. And then we're just going to use our for loop like we did earlier, but this time we're going to say, well, we're just going to use the for in 1 to 5, for I in 1 to 5, we're in the genes vector in the first position, add gene num's first element and separate it by a dash, and then store these in our empty vector. And then store these values for each run. And so when we do this and print the contents, you see that it indeed added that, which is pretty great. Alternatively, we could use genes and I in genums, because genums essentially has the values that we need to be able to pull up the gene of interest here in genes I. So essentially what that means is that since I is the integer here, which just matches the index position of the gene we'd like to modify, then we could have just written the code directly as is. Okay. Now, let's try and make the gene names. Again, let's modify the gene names, but this time adding letters. Okay, so to do this, again, just have my genes, and then gene letters, I'm using the letters function. I mean the letters vector, which essentially contains all letters of the alphabet, as you can see, and I'm just saying, give me the first 5. And again, we're creating an empty vector to work with. And this time, again, we'll use for I in 1 to 5, because we only want to change the first 5 elements, and use essentially genes and gene letters instead, with again the index position, and then store these in a new vector, which we have here. And then we can print the contents, and voila. So for loops are great, but you can imagine that each iteration can take a lot of time if, for example, not each individual iteration, but say you want to run a for loop but not just change 5 elements, change 10,000. Well, to do that, as you can imagine, this could take a lot of time. And so let's actually use the system.time function to find out how much time that would take. And if there's an advantage to using the apply function instead. So here, I'm just going to copy these. Right? So we can just print the contents. So the first 6 contents using the head function. So genes 2. Okay, so you can see we've got our genes. Essentially all I'm doing is I'm sampling my genes function. Okay, so this is really important, because if you do not, for example, if you just thought that, oh, I'll just save it in new gene names directly, well, what you would have realized is that it's just going to store the last value. And that is because the variables are changed each time. Like, you input a new variable each time you ran the for loop, and not necessarily stored it. There's other ways you could have written this for loop, and I'll leave it up to you for homework to figure that out. So, and I'll give you a quick hint. You could have created a vector that has 6 elements, and then added each gene name to a different index position. Okay, please ignore or cut out that part if it's too much. It's just like a little exercise, but you can just take it out. Okay. Okay, so we've printed the contents, and now let's try and make the gene names unique. So we could do that by saying, for example, gene names here. So we're storing our genes. Sorry. So now for our next example, let's make the genes unique by adding values 1 to 5. And so to do that, we'll take advantage of the sec function. essentially what I did was I used a sample function just to sample the genes, vectors, and take 10,000 elements from each. And then we're going to run our for loop. But this time we're going to use the system.time function to actually time how much CPU time, etc. that it took. Okay, so again, we write our for loop, but this time it's actually within the system.time function. So here we go. Okay, so as you can see, it kind of gives us an idea of the time used. So if you want to know more information, you can just consult the help page. So essentially, it returns the CPU and other times that the expression or the function used. Okay, and so let's see. We won't look at all the elements, so let's just take a look at our tail, and as you can see, it did indeed work. So instead of using a for loop, we could have just used the apply function. We would first create a data frame using genes2 and genes letters 2, and let's just inspect the first 6 lines, and as you can see, this is what it gives. And then we could run our system.time on the results from the apply function. So in this case, we're using function x, paste x1 with x2 separated by dash. And that's because we're using the apply function with 1 here, which means by row. So essentially, take the df data frame, go by row, and add the first column to the second column, separated with a dash. And as you can see, it took a lot less time. And I didn't save it here, but let's just compare this directly. Here we go. And you see, so user 0.068 compared to 0.457, etc., etc. So you can see it's much quicker to use the apply function when you can. Of course, reusing for loops are actually quite intuitive and easier to write, but once you get the hang of converting these to something that an apply or apply-like family members could run, you will realize that your code will run much more efficiently. And this is really important for when you have very large data sets. So as I mentioned earlier, the system.time function is quite useful because it returns the user, system, and total elapsed times for the currently running R process. And so what you might conclude is that ideally you might want to work with apply functions when you work with really large data sets compared to the for loop. So in summary, this video showed you how to work with the for loop and showed you how to use a system.time function to be able to have an idea of how much time it takes to run your for loop, but also, for example, the apply function. And as we saw, for really large data sets, it might be more interesting to write a function so that you can use the apply function over a for loop. And so now in the next video, we'll be looking at if statements and the if-else function. Hi, and welcome to the fundamentals of R programming. In today's video, we'll be looking at the if statement and the if-else function. More specifically, in this video, we're going to take a look at how to use the if statement, how to use the if statement with the else if statement and else statement, and how to use the else if function. Okay, so before we begin, I just want to explain that the if statement allows you to evaluate a condition, and if it returned code in the brackets will be executed. You can add the else statement to your if statement if you would like to execute a block of code if your condition returns false. You do not, however, need to always have an else statement. You could just write an if statement if that's what you need. So let's start with a very simple if statement. So we're defining the variable x, and we're saying it's equal to 12. And then we could test if x less than 12. And again, we can use the brackets, or for very simple statements, you don't have to use them. But I'll just include them so you remember to use them. So if x is less than 12, you can say print x is less than 12. Okay. Okay, so let's run this code in R, and as you can see, it didn't print anything. Now, say we were to say if x less than 12, right? But instead of less than, say less than or equal to 12 is less than or equal to 12. So let's do this. And as you can see, now it actually prints x is less than or equal to 12. So what if we want to use the if statement but an else statement? So say x less than 12, and now we're going to use code as follows. Print x less than 12. And then we can say else, so use the else statement. Again, open brackets, print, x is not less than 12. Okay, so now when we execute this code, it will have an option. So as you can see, when it evaluated x not equal to is less than 12, it returned false, so it didn't run the code. And because there was an else statement attached or following the if statement, it was able to execute the following code: print x is not less than 12. So this is very useful when you're writing your own function or your own scripts for that matter. And you don't even have to just use these types of statements. You can, sometimes you can say, for example, you have some genes here, okay, and then you just, let's call them, say, Mick, and let's say CC and D1, and finally we'll have TP53. Okay. And instead of genes, let's call them proteins. Proteins. Okay. So let's just store this, proteins. And let's say, well, we can also use the if statement with actual, for example, using character vectors. For example, let's say if proteins. So, and this time you're going to see it's going to give us an error message, but I want you to understand why. If proteins is equal to, say, CC and D1, okay? And this time I will just write print yes. Okay, so you see this time I didn't include brackets, but it's just so you have an idea that you can, do this. And what you see is, oh, warning message, there's more than one condition. That's because you can't just test a full vector. You'd have to test each element in that vector separately. So to do that, we can take advantage of our for loops like we did yesterday. So for I in, we can take advantage of writing for loops like we did in our previous video. So for I in proteins, and then we can just copy this statement. Okay, so now we can say for I in proteins, if I is equal to CCND1, press yes. Print yes. And now you see it returned yes. So we know that one of our elements returned, had one of the elements in the proteins vector contained. Okay, so to do this, we will say For example, if, and again, we're going to take advantage of our for loop. So actually, let's just copy that here. So for I in proteins, if I is equal to, let's say, A, N, B, S, C, print yes, else if I is equal to banana, and then finally you would say print this is not a gene, and then finally we can end on else, print your protein of interest is not found. Okay. And so let's evaluate these statements. So let's make sure, so you'll see that we're missing, so for I in proteins, so here we're missing an extra bracket. So it can get pretty confusing. So I think in this case, for clarity, we should just write it as is. So for clarity, we're just going to use the following indentation. And now you can see that we have all our brackets. And now you'll see that for each iteration of the loop, it returns your protein of interest is not found, because none of them was evaluated. And now for our last example, let's change this here to make. Okay, so you can see, and now let's run, and you'll see that the first element, yes, it contained Mick, and the two other ones didn't. And for fun, let's save our proteins, or combine our proteins vector with the word banana, and then rerun this code, but this time saying for I in Y, and evaluate the following statements. So here we've created Y, and now we're just going to run that block of code. And as you can see, it returns this is not a gene for banana. One thing to bear in mind using these Boolean statements is that it's going to look for an exact match with Mick as follows or banana as follows. So if you don't want to necessarily restrict yourself to exact matches, I would suggest either using the grep-l. So remember we learned that in an earlier video where it returns a logical statement, and the advantage of using grep functions, so here are related grep functions, so is that you can actually ignore case and you could use pattern matching instead. So that would be my suggestion. Okay, but at least now you should be able to write very simple, or to be able to write for loops. You'll be able to use the if, and else statements. Now, R actually has a really great function called the if-else function. And what this allows you to do is to test a statement, and if it's true, it will return the first element. So for example, I think it's easier to visualize this. So say we use if-else x less than or equal to 12 If it's true, I want it to return red, and if it's false, I want it to return blue. And you see it returns red. The if-else function is really great when, for example, testing conditions to determine which color you want to plot, for example, your line. So here's an example of this. So let's use the plot function. So let's do plot h equal to x. Whoops, sorry. Okay, sorry about that. So please edit out the part that generated an error. So say, so this is very, very simple, but it's just one dot. So plot x. So you can see it generated the plot, and now we can color that plot depending that dot depending on its value. So col equals, and then we can use our if-else function as follows. And as you can see, it colors it red. So you can use a more generalized statement and to be able to test each of your points separately and color each dot accordingly using the if-else statement. So this is a nice little example of how you can choose your colors based on values. So I will leave it as homework for you to see how you could generalize this statement for, say, multiple values. And as a quick hint, okay, so please so in conclusion, blooper, in summary, in today's video we learned how to use the if statement, the else if statement, and the else statement, and we also learned how to use the if-else function. And now in the next video we'll be looking at the while and repeat loop and how to use the break statement with these. Thank you very much, and see you in the next video. Hi, in today's video we'll be looking at the while and repeat loop and how to use the break statement. More specifically, in this video we're going to take a look at how to write and use a while loop, how to write and use a repeat statement, and finally how to use the break statement with the repeat statement, and finally how to use the stop function. Okay, so in our first example we're just going to write a simple while loop. So for that we're first going to store the value 2 in x because we want x to equal 2. And then we're going to write, in contrast to the for loop, the while loop allows you to repeat a block of code until the condition that you're testing returns false. So if we look at the following example, instead of writing while, instead of using a for loop, which runs from, for example, 1 to 12, or whichever values you choose to interrogate, the while loop will test each value of x until it is less than 12, in which case it will add 4 to x and print that value on the screen. So as you can see, it's kind of written like a for loop, except that now we're looking for the statement to be false to stop the execution of the loop. Okay, so as you can see, if we start with x equals 2, it adds 4 each time and prints this value to the screen while x itself is less than 12. So remember, after the second iteration of the loop, the value of x was 10. This is still less than 12, and so it adds 4 again, and then now x is 14. And when it tests, if x is less than 12, it is no longer true, and so it stops. The repeat statement is very similar, except that it will repeat the code or the block of code indefinitely until you tell it to stop, or you tell it to break, in other words. And so typically the repeat statement includes an if statement with the break line. But this is not required. But most of the time you will see this combination. And so let's look at a new example where let's keep x as is. So if we print x, you'll see x is 14. And now we're going to add 4 to x and print this value until x is greater than or equal to 20, in which case it will break the repeat loop. And so stop the repeat loop. And as you can see, it had time to repeat the statement or the block of code twice, because once x was equal to 22, the third time it tried to run the loop, well, it realized that x is now greater than 22. X is now greater than 20, and so it broke the statement. Alternatively, you might want to use the stop function. So unlike the break statement where you combine an if condition and then test that condition and then break, you could potentially say stop. To learn more about the stop function, we can open it up in the help section, which you can view here. So essentially, instead of doing, please edit the video recording. So if x greater than equal to 20, then we can say stop and execute or include a message, which we will say, warning, x is greater than 20. Okay, and for example, now x, before we run this code, we will set back x to a smaller number, say x is equal to 2, and then run this block of code. And as you can see, when we use the stop function, we actually get an error. And it says, error, warning, x is greater than 20. So essentially the stop function not only will stop the execution of the block of code, but it will also generate an error message. And this is very important or useful when you're generating your own functions or writing your own R packages, so that you know when to generate an error message depending on how the user is utilizing the code. So instead of writing it as is, what we could have said, which would be a better, say we were writing a chunk of code to use in our program, and in this case, before even running the repeat statement, we could check if x is greater than or equal to 20 and then say, warning, too many iterations, or not even warning, but we could say too many iterations required. Okay, and this is because, so if we run this, as is, now it will test first thing. And as you can see, after x was equal to 22, it stopped and it's like, error, too many iterations required.
This is useful, say if we wanted to include this statement in a block of code that we're writing, and say the user enters x is equal to 200. And now, once they try to run this code, they're actually immediately getting an error message to say that there's just too many iterations required. And that will save you from repeating the statement indefinitely, which is a danger with using the repeat statement. Okay, another useful statement that is used when writing blocks of code is the next statement. And so the next statement allows you to skip an iteration of the loop if the condition tested is met. So in this case, we're going to start with x is equal to 1, then we're going to run a while loop while x is less than 5, add x plus 1, store this value to x, and then when and if x becomes equal to 3, then skip this iteration of the loop, and then the last thing to do is to print x. So let's see what this actually looks like when we run it. And as you can see, so we started with 1, then it had 2, it skipped 3, and then print 4 and 5. Okay? And this is because the first time x was equal to 1, it was less than 5. We added 1 to it. It now became 2. If x is equal to 3, it wasn't true, so it went on to print x. Next time, then we're starting with x is equal to 2. We add 1. It's now 3. Since it's 3, it skips this iteration of the loop. So, and when I say it skips the iteration of the loop, what I actually mean, it will skip all statements below the next statement. So as you can see here, what occurs after a test is print x, so it will not print x essentially. And then it will add x plus 1, now will become 4. This will no longer be true, and it will be able to print, etc. Okay. So now you can see how we can combine these different statements. So in this example, let's start with x equals to 5, and then say, well, x is greater or equal to 5, then add 1 to it. If x is equal to 7, then skip. Otherwise, print x, and then if x is greater than or equal to 10, break the loop. And you can see what this looks like. Maybe running the code as follows, and you can see that it indeed skipped 7. So if x is equal to 7 was true, it actually skipped all this code below and then restarted the loop. So we'll just end this video by using a nice little example of how to write code to be able to evaluate the sum of natural numbers without using a formula. And so this code was modified from program is, which has lots of nice examples. And in our case, we are going to just start by saying the number is equal to 15. So we want to actually get the sum of natural numbers for 15. And then what this code does first is it tests if the number is less than 0, in which case it will ask, or it will print, enter a positive number. If this is not true, then it will execute. It will execute the else block. So else will say the sum starts being equal to 0, and then while the number is greater than 0, we add sum plus the number and store it into sum, and then we'll say number minus 1 and store this value into num. So essentially we're counting backwards. So we start with 15, and each iteration of the loop will reduce this number by 1, all while adding the sum will add this number and store it into sum. So essentially, let's just take a look, and then once the code is finished, it will print, paste, and the number is, and it will actually tell you what the sum is. by using the paste function, so that you can include this block of text with this variable, or the contents of that vector. Okay, so we already said num is equals 15, and then let's run this block of code, and then you see the answer is the sum is 120. And so really what's important to realize with this code, or to remember, is that when using the while statement here, we're testing that it has to be greater than 0, because it has to be like a positive number. If it's not, if the user puts in a negative number, or once the value, if the user puts in a negative number, then it will automatically print this message. Or else, if the user put a positive number, it will start with storing sum equal to 0, but they could have just as easily did sum is an empty vector, right? Like we had seen earlier, and then it will use the while statement to actually run the loop indefinitely until the number is, once this number becomes negative, it will stop running the loop and end by printing what the sum is. So in summary, in today's video, we learned how to write while loops and repeat statements, and we learned how to integrate the repeat statement with, for example, a break statement. We also learned how to integrate the next statement with the while loop, and finally we learned how we could use the stop function to generate error messages when using these types of loops. And so in the next video, we'll be learning how to write our own function. Hi, and welcome to Fundamentals of R Programming. In today's video, we'll be writing our own functions. More specifically, in this video, we are going to take a look at how to write a function, how to write and use arguments, and how to use the 3 dots in your function. How to use the 3 dots in your functions. Okay. So I think we've already alluded to how to create functions very quickly in our other videos, but today's video will really help you to understand how to create your own. So if we look at a help page where, let's just say we say mean, you can see here that most functions are defined by arguments. And so for the mean function, we have x, which takes an R object. And then the 3 dots suggest other parameters or other arguments that can be added as well that will be recognized by the function mean. And these arguments include trim, na.rm, or the 3 dots in this case, further arguments passed from other methods. So you can use those arguments. But before we go into details of how to create more extensive functions, I think we'll just start with a very basic function. So in this case, let's say get mean express values. Okay, so in this case, we're creating a function called getMeanExpressValues for expression values. Try and name your function something meaningful that you'll be able to recognize what the function does, or feel free to comment your code by saying, with this function, I will calculate the mean expression values. That way you kind of have an idea of what your function does when you go back to your code. So here we'll just invent some expression values using rnorm. So if you want to see the parameters for rnorm, you see we have x. So for rnorm, it's the number, sorry, of values we'd like to simulate with a mean of 4 and a standard deviation of 5. And these will be our chains here. So we take a look at our values.
Yes, there we go. Okay, and so technically if we wanted the mean of our values, the simplest and quickest way would be mean and then values. Okay, and then we got the mean of these 5 genes. But say, for example, we create a data frame, because most of the time you'll be working with data frames, and we say data frame okay, so you can take a look at your data frame object. Say you want to work with this table directly. So you want to make your own function that will recognize this table and do the calculations that you want it to do. So in this case, we can create our function, which is what we will do in this example. So just to simplify my comment line, I just did this, and then here we say function. And so we could say function x, but in this case, I want it to remember it's a data frame, so we can say df, or so we don't get confused. And then we can define this function as so mean express is mean df values, and then we return the answer. Okay, so that's a very simple function. Normally your functions would be a bit more complex, but it's tailored to your needs, and that's the advantage of creating functions. So once we've created that function, now we can actually use it with our data frame as follows. And you can see it gives us the same answer as earlier, which is to be expected. But instead of, doing this process in my lines of code and then getting the answer, I could create a function so that, say I had multiple data frames, I could just loop through these data frames using these functions, which is pretty neat. So it's very helpful to avoid rewriting code extensively, because once you've created a function, you can just call that function, and you can use that function in a for loop, etc., or even with the apply and other related functions. So for example, let's just create another one, df2, where, I can illustrate this example. So this time, I will just say data frame genes values equals, this should be here. Okay. And then we can see what we entered in df2. Okay, perfect. So these are the values in df2. And now I can create, for example, data frame list, and then say list A equals df, B equals df2, right? And so now I've created a list of data frames, right, that you can see here, right, A and B. And then I could, for example, say for I in 1 to 2, I could run this function on each data frame stored in my list. do that. Okay. And you can see it's the same. Let's just double check if that's true. Maybe I should have changed the mean. Oh, yeah, that's true. Because I simulated the same. Here. Yeah, it's the same. So for the sake of argument, like we can change this mean here to 5 and the standard deviation of 3. So you can get a different mean. If we rerun this code now, so I realized the mistake is actually because I called df directly instead of the name of the argument in my function. So that's very important, and that's a good example for how to troubleshoot, because technically the mean shouldn't be the exact same thing if I changed the value simulated. So now, really, by just calling df in my example, because the object exists, it's using df. However, if we were to clear the objects in our environment, then we would get an error message. So now that I've rewritten the function and created this list, it should work. Exactly. And now it gives me the right means for each one. So, and that you could have also done by just, for example, running the function on each one of them separate. So here for df, here for df2, right? And you get the same values. Or you could have taken advantage of lapply, or sapply in this case, because I'd like to return the values as vectors, and I would say, well, I want to use dflist, and I would like to apply this function. You see? And there are the values. So just a quick recap. So here what we did was we first created the genes, and then we had the values that we simulated in our first in the first case, and then we created our data frame from these vectors. Then later in the example, we wanted to create a second data frame. So in this case, I just made it directly. So I used the same genes, but this time I simulated values with a different mean and a different standard deviation. Okay, and then we created the getExpressValues function, which looks for a data frame that we define as expdf, so expression data frame, and then we take the mean of expdf and using the column values, and then return the results. And that's what we did, and then we showed that we could create a list and then use a for loop to use our function repeatedly, or that we could call our function for each data frame separately, and finally that we could have taken advantage of the sapply function to again use our user-defined function to return the results for each data frame stored in our list. Okay, so the next thing we're going to do is create additional arguments. So for example, instead of writing the function like this, we could have written function expdf and then say column use as an argument, which would tell us which column to find the values. And then here we would modify this as expdf column use. So here we will return the column to use, and then it will return the response. the answer. So we can call this a second function that we call 2. So again, just so we know what it does, it returns the mean for data frame using column use equals, for example, 2, or to define where the values are stored. Okay, and so here we could have reran all those examples as above, but now we're just going to run it once. And let's say we wanted to run this one on df. So if we just run it like this without changing anything, we get an error message because it can't find the values for column use because we absolutely need to define it for the function to work. If we wanted to save ourselves this error message because most of the time the values will be stored in the second column, or by default I want it to look in the second column, we can predefine this as 2. And now if we rerun our function, it now works because by default it will use column use equals 2. Now say we wanted to use a different column. So let's create or modify df and say cbind df with values 2 equals our norm 5, 3, 4, and 6. So you see I don't have to spell out each argument, I can just use their position. And so if we look at df, now we have 2 columns with values. And so now, instead of using the default second column, I would like to specify that I would like to use a third column. So here I could either write it out completely, in which case it will calculate the value, or I don't even have to use this because I could just use the position and it will return the right answer. Okay, and then finally, say we wanted to add that 3 dots. The 3 dots will allow us to use actually call, other parameters or arguments that are found in functions called in our function that we created. So let's call this 3 and let's give it a test. So I think if we just run it like this, and this time we want to use the na dot remove equals, instead of it being by default, if we look at mean, it's false, we say we want it to be true. Okay, so now we need to have 3. So let's whoops. Okay, so first let's define the function and say we wanted to run it as is. Let's see if we get an error message. No, we don't. But I want to be able to show you that the example actually works. So let's change one of the values in df. So let's change to 2 and put an NA. Okay, so now if we look at df, there's an NA value. And so let's now use NA equals true. And instead of the third column, we'll use the second column. And now you see our mean is 4.06.
And let's see what happens when we say na.rm equals false. We get na. That is because if we say na.rm equals true, in the mean function itself, it tells it whether or not na values should be stripped before computing the mean. So in this case, we stripped the na value, and so we calculated the mean for the remaining 4 genes. But if we say na.rm equals false, well then now we don't remove it, so it's not going to compute the mean. So here you see is a good example of how we use the 3 dots function, because without the 3 dots function, I would have to have specified na.rm equals true or false directly in my mean express line here, which I didn't. So instead, I wanted to be able to just call that argument as an argument in the function I created to return these values. Okay, so in summary, in today's video, we learned how to write functions and how to look at or modify parameters in our functions and actually call other arguments or parameters in the functions that we use using the 3 dots notation. And so in the next video, we'll be learning or looking at general programming and debugging tools. So thank you very much for watching, and see you in the next video. Hi, and welcome to the fundamentals of R programming. In today's video, we'll be learning some general programming and debugging tools. More specifically, I'll just be giving some general programming advice and debugging advice to help you write your own code. And we'll briefly go over the traceback function and debug function. So before going into some debugging advice, some very general advice I can give you when writing your own code is that you need to have a clear picture of what the problem is. Once you have a clear picture of what that problem is, or what questions you want to address or answer, then you can start to think about the steps that you would need in order to specifically address that question with your program. And so, for example, if you do a simple experiment, you treat some cells with or without a drug, for example, you collect the data. So this could be expression data, but this could also be counts or any other measure, any other way of measuring whatever variable you're interested in. And then so you store this information in, for example, a table in Excel, and then you need to think, well, how am I going to write a script to ask what the mean expression is, for example, of gene X in both conditions, and for example, what are the top genes that distinguish condition A from condition B, for example. So these are very broad questions, and once you've done your actual experiment, well then, and collected the data and have the tables, well then you need to think of how you're going to structure your R code to ask those questions. And so you start to break down the problem into steps. And so these steps would include A, loading the data into R. So am I loading a text file? Am I loading expression data? How do I need to treat my expression data? Do I need to log transform my values, or do I use them as is? Once I've uploaded my data, do I need to create or subset my table into a data frame, into a matrix? How am I going to visualize my data? So those are all questions that you need to ask, and then you can actually write out each step as a draft and then draft your code based on those steps. So for example, I read a text table, so I'm going to need the read.delim function. Next, I need to calculate the mean on a per column basis. Okay, so I can use the mean function to do this. Oh, but I need to make sure I segregate by groups. Okay, so I'm going to need a factor to segregate my table or subset my table into different data frames and then use the mean function. So you see, that's essentially the thought process that you need to have when starting to work on your own R scripts. Another small piece of advice I can give you when you start to write your own R scripts to address your research questions is to try and have an R script that you have all your generic functions, or essentially try to make your functions as generic as possible so that you can reuse them at a later date. So for example, you can have generic functions and then just source this file or copy and paste the functions that you need into your R script, and then you start to build essentially these tools that you can then go back to when addressing other questions or working with other data, but then you don't have to rewrite your functions always from scratch. So now on to the trickiest part of programming, which is the error messages and trying to solve your bugs. So the first thing you should do is try to recognize that your code has a bug. So just because you run the code successfully doesn't mean it's giving you the right answer. So you need to really make sure you run, for example, your controls. So, oh, I know that, the mean of x should be greater than 20, either because you ran it yourself using another program or in Excel, or because you just expect it to be greater in condition A than B. And if you're not seeing that result, well, then you can start to say, oh, maybe there's something wrong with my code. Maybe I mixed up variables, etc. So really, the first step is really to recognize whether or not your program has a bug. And one of the tools I'm going to show you real soon to see whether you have a bug or not is the debug function, because that will allow you to run each line of your code separately and actually view the contents of each variable you've created. Next, when you have a bug, well, the next thing you should try to do is try to make the bug reproducible so that you have an understanding of, oh, where's the error coming from. So it's easier, that is because it's easier to fix a bug that you know how to trigger. So if you can trigger it, then you're more likely to be able to fix it. Next, you need to identify the cause of the bug. So even if you get error messages, sometimes the error message can be very generic and you're not quite sure what they mean. So for example, very often error messages can be triggered because, for example, you reference an index that doesn't exist. So say you uploaded a data frame, you forgot to include the header, so header equals true, and so now you have an extra line and you're calling the first line and you're getting an error message because you're expecting integers and you actually stored strings in your first row. So that's one example, but other common causes of errors could be, for example, referencing a column that doesn't exist because you think your data frame has 20 columns, but it only has 19, or when you make test conditions, so for example, if x equals 12, well, you might just write x equals 12, and that is not the same as writing the Boolean statement x equal 12, which means does x equal 12, right? So small mistakes like that can really lead to error messages, and with time you'll start to recognize these errors more rapidly and will not make them. Or, for example, when your code is not written in a way that it deals with NA values, so it returns an error message. Next, to fix errors in your code, you need to be able to fix these, and then be able to test whether or not you have successfully fixed them. So that could be done by rerunning your code from scratch or loading new data, or even sometimes the best trick I find is to actually start from scratch. So close your R session or erase all the objects in your workspace and then rerun your code. Because sometimes if you have some of the variables lying around in your workspace, it will just use those variables and instead of giving you an error message. So you really want to make sure that you can run your code in a fresh new session in R. And then finally, look for similar errors elsewhere in your code. If you've discovered, oh, I've been using gene instead of the gene variable, instead of the genes with an S variable, and so I'm not actually using the right genes, then I want to go back in my code and change all those variables so that I'm using genes with an S versus gene without an S. So for example, you stored one gene in gene and then a vector of genes, and for simplicity, say you said gene A stores one gene and then gene B stores a vector of genes. Well, if you call gene A instead of gene B, you're ultimately not going to have the right results, or you probably made that mistake elsewhere in your code. So you want to be able to go back. Okay, so now just real quickly, let's look at some examples. So first, let's create a function. So here our function is called getMean plus 2. And so essentially it's a function of x where it takes the mean of your vector x, adds 2 to it, and then stores this value in y, and then it returns the value stored in y. And now to test our function, I'm going to create a vector called x1 that stores the values 1 to 4, and then run this code of this function. And as you can see, it returns the value 4.5, which is the value I expect. Now let's try our function with another vector, which we'll call x2, which has the values 2, 6, 8, and na. And then, because I just assumed that I can call the mean function's argument na.rm, which by default is false, I'm just going to say no, I'd like to use it for true. I'd like to use it as true. And as you can see, I get an error message. And this error message says that it's because it doesn't recognize the argument na.rm. And you might be thinking to yourself, well, na.rm is part of the mean function. Why can't I just call it directly? So one way to fix that problem is actually to go in and rewrite your code and then specify here na.rm equals true. But this means that it will always, every time it runs this function, it will always assume that na.rm equals true. And then rerun the code. But as you can see, I still get an error message. So why is that? So one of the things you could do is trace back. In this case, it will tell you, well, it's coming from the getMean plus 2 function, and that is because up on the first line right here it says na.rm, and I didn't actually put an argument na.rm. So even if here is true, then I would have to, for example, say na.rm this, and now let's try and see if it works. And now it works. So that is because I've added this argument. Of course, this is not how you should be writing your function, because like I said, here it's always going to be true, or you can potentially put na.rm equals true here and leave it like this. This should potentially work. Oh, no, not at all. It actually says error there's an error message because trim must be numeric of length 1. And now if we do trace back, so in RStudio it will actually give you that option, but if you're working in R itself, then you'll need to call the function itself. And so now you see, okay, so first one, second, so you can actually see the steps. In the first step, okay, it's fine. Second step is fine. But third step, mean.default x na.rm, and then it's returning the error message stop. Trim must be a numeric vector. And the reason for this is, with practice, you'll learn that, oh, it's because it's actually by just putting na.rm, which is an argument, by just putting na.rm, which is so essentially so I've actually made this function now way more complex than I thought it would be, because by creating an argument na.rm, it's actually not the same as using na.rm in the mean function, because by default, if I just put na.rm, it's assuming it's in the second position, and by default the second position is trim. So really the way R is interpreting it is trim equals na.rm. And because na.rm is logical and not numeric, it's giving me an error message. So if we did not know this and wrote this, for example, because you can also use 1 for true sometimes. If you're a programmer, you'll use 1 or 0 to represent true and false. And this time, if we rerun our code, in this case, then we get NA. And so you would think that, oh, I ran my function and it worked successfully, or it didn't actually, because I was expecting it to remove the NA. Where's the error coming from? Well, as is, can't just write trace. If we didn't have that error that we had before and used traceback, we wouldn't have recognized that, oh, it's because it's actually interpreting it as trim equals na.rm. And because na.rm is true, then it gave me that error message. But if I put a 1, it's not going to give me an error message because it's expecting a numeric of length 1. And so you realize that this is not what I meant to do. So the right way to write this function, or the correct way to write this function, would be to use the 3 dots, which we had learned earlier. So in this case, by having the 3 dots in our function and in the mean function, we can now call the arguments of the mean function by their name, and then we will be running into the errors that we've been running in the previous code. So let's do that here. Okay, so we've entered this function, and then now let's try and run get mean plus 2. And as you can see, it actually works. And if we said false, we get NA, which is what we expected. So you see how, if you're not careful, we actually would have ran a function that returns a result. This result is not what we expected if we had used this function here versus writing it in the correct way and getting the results that we're meant to get. So in our next example, let's create a function getResults here, which has multiple lines, and essentially it repeats x 4 times, stores these values in y1, divides y1 by 2 and stores this value in y, and then takes the mean of y and stores it in results. And because I want to be able to keep the options available for the mean function, or the parameters available for the mean function, I use the 3 dots in both cases. And so now we've entered that function. Now let's try our getResults functions on x1. As you can see, it returns y 1.25, and if I run it on x2, well, it returns NA because by default na.rm is equal to false. So let's change that. And as you can see, it returns the values. But what if I wasn't really sure what I was doing? So I wrote this function, but what if I wanted to make sure I knew what values were stored in y1, what values get stored in y, and then which values are returned? To do this, we could use the debug function. So here, if we look up debug in the help page, then we can say, well, the debug function takes a function, and here we're giving it getResults. And so now, every time I call the getResults function, it will enter into a debugging mode, which essentially allows me to run each line separately. So, for example, let's say we wanted to do getResults x2 na.rm equals true. Well, when I press enter, it goes into the browser, and it allows me to run each line at a time. So you can actually check the contents of each variable. So say if I go x, oh, well, now I know x actually has the values stored in x2, which is what I expected. Now if I press enter again, we're now at line 2, and so in line 2 I can check what x is. Well, x is x2, which is good. If I go to the next line, I can check which values are in y1. And now I can see, oh, well, y1 is actually returning 2, 6, 8, and 8, etc. And so, for example, if I meant to use the C function instead of the repeat function or rep function, then I would be able to see this here, because instead of, if I just use C, I would only have 2, 6, 8, and an A. But if I use the rep function with 4, then I would expect to repeat x 4 times, which is what we see. And so this is very useful, for example, to make sure that you understand what's happening at each line in the function you've created. And then let's go back to the browser. And so now we can check what's in Y, because now we're looking at line 4. And so this is what it returns. And then we actually see what's in 2.66. And so now we're exiting. So the debug function is actually a really great tool to be able to go back and actually check what's going or what's happening at each line. And say you don't want to always enter the debug mode, well then you just have to use the undebug, right? Undebug here. And then we put in our function, which is get results. And so now, if I rerun this line, here, I no longer enter that browser. Okay, so that's pretty much it. And so in summary, what I've shown you in this video is essentially how to use the debug and traceback function to be able to look for bugs in your program. We also went over some very general advice for how to create your own program. So really the importance is to have a specific question in mind and then design the steps needed to address that question and implement that in your script. And then finally, we went over some very generic steps you can take to try to solve bugs in your program. And now, since this is the last video for this section, I just wanted to summarize what you should have learned from these videos. Essentially, we went over the for loops and the apply function and how you can use the apply function to save time when you want to run a for loop, at least computer time, and which is really great when you're working with very, very large tables. We then learned how to use the if statement and the if else function. Then we went on to look at the while repeat loop and the break statement, and we also took advantage of learning the stop function, so how you can implement that in your code. We then went into how to write your own functions, and then finally we concluded with some general programming and debugging tips. So in the next section, we'll be moving on to statistics with R, or essentially how to evaluate probability distributions in R. So thank you very much, and see you in the next section. Hi, and welcome to Fundamentals of R Programming. In this section, we'll be evaluating probability distributions. More specifically, in this section we're going to take a look at descriptive statistics, the overview of probability distributions, how to fit probability distributions, and finally, how to perform other tests that are used to fit distributions. In today's video, we'll be looking at descriptive statistics. More specifically, we're going to look at some very basic functions that give you statistical information from your data. So we'll look at the summary statistics, the mean, median, variance, and standard deviation. So let's go on to our example. So before beginning this tutorial, you can either go through the steps to load the example. So this is actually taken from gene expression data that's available on ArrayExpress, and then run these lines of code here. Otherwise, you could just load the RData object provided on the website directly using the load function. Either way you choose, once you've loaded the data or reran the steps here necessary to generate the expression data set, you can start. So in this case, I reran the code from scratch, but you could just load the data. And so essentially, if we look at the mllpartner.mx, so essentially what this is a matrix for MLL expression data, and you can learn more about the experiment by looking up this ID in ArrayExpress. But for the purposes of the tutorial, we'll be using the expression data to look at some of the functions used to get basic information or basic statistical information. So if we look at the class, you'll see it's a matrix. If we actually look at the 3 first columns, we can use the head function. As you can see, you have the GSM ID, which is essentially the sample ID, and then you have your probes. If we look at the dimension of our object, or the dimensions of our object, you'll see that there are over 54,000 probes and 42 samples. If you look at the probe A object, you'll see if we use the summary function, it will tell us the minimum value, the maximum value, the first, median, mean, and third quadrant. If we look just at the first 6 values in probe A, you can see the values stored in probe A using the head function to look at the first 6 values. So here, in this code here, we use the summary function to kind of summarize the contents in our probe A vector, but we could also do this for our expression matrix as follows. And this time, you can ignore the warning messages, but it actually goes through every single sample. And so by each column of your matrix and gives the same information. So the minimum, the first quadrant, median, mean, third quadrant, and max. And this is very useful to kind of have a feel for what your expression values look like. You can also get the individual information using the functions that return the information. For example, the minimum value, you could use the min function, which is 4.21 for probe A. You can get the maximum using the max function. You can get the mean using the mean function. You can get the median using the median function. And if you want to remember what summary gave you, you can enter it here, which is essentially the same values. If you want, you can also use the quantile function, and by default, the quantile function is 0, 25, 50, 75, and 100%, but you can actually change those percentages with the probs argument. So here the probabilities that we're interested in is 10%, 20%, 60%, and 90%, or the 10th percentile, 20th, 60th, 90th. Instead of just getting the mean, you might be interested in just rounding some of the values, because as you can see, it's a bit verbose. So you could use the round function, and then the second argument allows you to specify how many decimals. So here you see we've got 2 decimals, 4.77. If you need help, let's look at the round function. So here you go, round and digits. And so essentially our second parameter here is digits, and we want 2. So now let's examine some basic statistics. So let's first create a data frame where we have the expression values for probe A and B, and then drug response as a factor. And so as you can see, expression for probe A, expression for probe B, and then drug response, success, fail, like shown. And so now, if we use the by function, which we learned about earlier in our course, we can say, well, with the data frame and using the drug A response factor, summarize. So essentially, we'll summarize expression values by response to drug. So drug A response. So where the drug A response is a fails, you have an idea of the expression values. You know that they're 21. And here you see the minimum expression, maximum expression, and then you could also look at the successes. So we had 21 successes, and this is what the expression values look. Then you can get the range. So you could do this by just saying max minus min for probe A, but a better way would be just to use the range function as follows. Right? And then we could also get the mean and standard deviation using the SD function, and the variance using the var function. So really, there's a bunch of basic statistics or basic information you can get from your expression object just using these functions. Or even better yet, just by summarizing the information using the summary function, or if we're interested in a particular response, we can divide that. We can actually look at the statistics by factor. So in this case, our factor was drug A response. So now that we've very briefly gone over how to look at descriptive statistics, variance, standard deviation, etc., we just really went over the functions that are used and how to get summary using the summary function. We'll now be able to move on to probability distributions. The next video, we'll be looking at an overview of probability distributions. Hi, and welcome to the Fundamentals of R Programming. In today's video, we'll be looking at an overview of probability distributions. More specifically, we're going to take a look at probability distributions in general and how to work with them in R, i.e. we'll be looking at the density, the cumulative distribution function, the quantile function, and random variate generation function for many standard probability distribution. For example, the normal distribution, but also the Poisson distribution, etc. We will also learn the prefixes used in R to be able to call these functions by combining the prefix with the name of the distribution in R. So for example, the P prefix is used to call the distribution function, Q for the quantile function, R to simulate random numbers, and D the density function. And then finally, we'll conclude by looking at some examples working with probability distributions in R. But before we begin, as I mentioned, you can combine the prefix with the probability distribution R name. And so, for example, the beta distribution is called beta in R, binomial, binom, chi-square, chi-sq, etc. The normal, which I haven't included here, NORM. And so for each probability distribution, as displayed here, which this is just a very short list, but there are many more, you can obtain the function that generates the mass or the probability function by adding the D prefix to the R name shown here. So for example, we could get the mass or probability function for the beta distribution by entering d beta. Next, if we were interested in the quantile function, we could add the prefix q to the R name shown here, and then we can get random or simulate random numbers from these distributions, for example, by adding R. So say we wanted to simulate numbers from the Poisson distribution, we would use R plus. And then finally, we could use the P prefix to get the cumulative density function for any one of these distributions. For example, say we wanted the cumulative density function for the uniform distribution, well, we could just add P to unif, so P unif. So I hadn't included it there, but there's actually a variety of distributions that you can work with, including the normal distribution. So here's a short list of some of the distributions available. And here it's just, if you're interested in more information, in this case we want to work with the normal distribution, we can click here. And as you can see, if we add D to the norm R name, then we get, we can use the dnorm function, pnorm, qnorm, and rnorm function. So let's start with the simplest functions to apply to probability distributions, which is the R functions. So rnorm to simulate values from the normal distribution, and in this case we're simulating 10 values where the mean is equal to 2 and the standard deviation is equal to 5. And this is important because, as you see here, n, mean, and standard deviation. So those are the three parameters it takes, and we get our values. We can also do the same for the Poisson distribution. So the R name for the Poisson is Pois, and then we just combine the R prefix. And as you can see, I've simulated 7 values with a lambda of 4. And then finally, let's simulate some values from the binomial distribution. In this case, if we go back and go to the binomial distribution, you see that our binomial takes n, the number you want to simulate, the size, and then size meaning the number of trials, and then the probability of success. So here, probability of success. And so here we go. So here our probability, for example, a coin toss would be 0.5 is a probability for success. As you can see, we've simulated values here. We've simulated 7 values here. Okay, so that's the simplest function to work with. And now let's go back to the normal distribution and see how to plot, for example, a normal curve. The example we will be working with we'll be working with a normal curve that has a mean of 7.5 and a standard deviation of 1.5. So first thing I'm going to do is get my x value. So I'm interested in getting 100 points between 0 and 16. And to facilitate this, I'm going to just use the sec function between 0 and 16 and a length of 100. And so now I have 100 values stored in x that begin with 0 and end with 16. We have values between x values between 0 and 16, and we have 100 of those values, or 100 of those points. And then we're going to use the denorm function, which, as I mentioned earlier, is the density function, and you can get more information here. So denorm gives the density. And I want to calculate or get the values for each value in x. And again, my normal distribution is with a mean of 7.5 and standard deviation of 1.5. Okay, so if we look at the first 6 values here, you will see them right here. And then now, let's actually plot these values. So if we remember, so for x we're using our values between 0 and 16. So for x we're using our values between 0 and 16, and then for y we're actually plotting the density for these values that we've calculated using the denorm function. And so here I just decided to call the plot water drank by school children less than 12 years old. I mean, it could be anything. And then here, we can use the pnorm function here to get the probability that, so essentially the area under the curve from 4, so 4 would be right here, right? So from 4 to about 0. And to do this, which is essentially the probability, so we use the pnorm function. Again, I give the parameters for my normal distribution, and here we see lower dot tail equals true because we want these values here and not the upper. And so as you see, the probability is 0.0098, etc. So that's essentially the area under the curve. Now we can look at the quantile. So for example, what is the value for the 65th quantile, or 0.65? It's 8. So if we look at 8, around 8 here, we would have, what would be the 0.65, or 65th percentile. As expected, if we look at the 50 percentile, which is essentially the mean, or median in this case, because it is a normal distribution, so they're equal, it's 7.5. And now, for example, let's get the 95th quantile for this distribution, which is 9.96. So here. So let's say we wanted to actually highlight the values for the 95th. So now, let's plot the cumulative probability distribution. And so do this, we can use the pnorm function, as we did, but this time we're calculating the values for the probability for each value stored in X. So remember our values that we have between 0 and 16. And then plot these values. Here we go. And then now we can use the plot function as follows. So this time our y is these values here stored, our pnorm, and as you can see, the cumulative probability is shown here. Next, we can plot our density like we did before, but this time instead of just plotting these values, we're also going to highlight the 95th percentile. So remember when we looked at the 95th percentile, which if you remember here, it's this value here. So to be accurate, instead of writing it out as our lower limit 9.97, we could have also just written qnorm 0.95, but you know, we can go approximately. So let's just do 9.97. And then our upper limit, in this case, we're just going to show 15, but we can actually go to 16 if we wanted to. And then now I want to return all of the values of X that are above our lower limit, which is 9.97, and less than our upper limit, which is 16. Okay, so if you look at I, it's actually a logical vector. All the values of X that do not meet the condition is false, and all the values that do meet the condition is true. And then we're going to use the polygon function with these upper and lower limits, and then we're going to color it red. And as you can see here, and we're also just going to add an add line, which will make a gray line n equals 0. And as you can see here, I've just highlighted the 95th percentile and above, and shown the area under the curve as red. And so what if we wanted to know the exact probability? Well, we can go back here with our pnorm function, right? And in this case, we're interested in the pnorm dot 97, right? Where we're interested in the lower dot tail is false. And it's 0.05. Okay, so this is just an example of how you can play with probability or create curves, and so you see the area under the curve is 0.05 approximately. And if you remember your statistics, this shows you essentially what part. And so here we've just kind of highlighted that area. So if the area on the curve then becomes 0.049 or 0.05. We can actually use prefixes R, P, Q, and D to look at different functions associated with a variety of standard probability distributions that are available in R. And in the next video, we'll be looking at how to fit probability distributions. So thank you very much, and see you in the next video.
So hi, and welcome to Fundamentals of R Programming. In today's video, we'll be looking at how to fit probability distributions. So fitting probability distributions in R. More specifically, in this video, we're going to take a look at how to fit normal distributions with the QQnorm function, and how to take advantage of the QQline function when assessing or fitting theoretical lines through our fitted distributions. Then we will also look at how to fit other distributions, for example, the gamma distribution, with the fit dist function that is part of the mass package. Finally, we will look at statistical tests that are used to assess the fit. For example, the Kolmogorov-Smirnov test, which can be done with the ks.test function, or the Anderson-Darling test, which can be performed with the AD.test from the NOR test package. So let's look at a few examples on how to fit probability distributions in R. So before we begin, I just want you to reload the example expression data, so the MLL data from video 5.1. If you don't have that data, or if you haven't watched video 5.1 yet, you can go through these lines of code, and then you can save this object so that you can use it in the first video. Otherwise, you could just go back to the location where your video is found. In my case, I'm going to do this, and then load the data directly. So if you look at the objects present in your session, the ls function, you'll see we have probe A, probe B, and our matrix that we created in the earlier lines. If you'd like to know more information about this particular study, you can go on ArrayExpress and search for this ID here. Otherwise, you can just take a look at video 5.1 and you'll see how we went through these lines of code. And now we'll start here and learn how we can fit our sample data to theoretical distributions. And so, for example, you may want to see if your sample distribution fits a normal distribution using a quantile-quantile plot. So, in this case, for the normal distribution, R already has a function that allows you to do that, and that's the QQnorm function. So let's give it a try here. And as you can see here, this is what we call a quantile-quantile plot, so, or QQ plot. So here you have your sample quantiles, and here you have the theoretical quantiles. And so now we can add a theoretical line for our normal distribution using the first and third quantiles with the QQ line function. And so here we go. So again, we're saying we're using the probe A, we're taking distribution Q norm, and then probabilities first, so 0.25 and 0.75. And as you can see, this is our theoretical line here. Now say we wanted to, so you can assess the fit to see how well it fits. So you'll see that in the middle here, it fits really well, but as you go on to the edges, it starts to not fit so well. So now let's, for example, test if our probe A data actually fits a gamma distribution, for example. For this, we need the mass package, so please make sure to install it. It's available on the CRAN, so C-R-A-N, or if you're in our studio, you can install packages. You can actually search for and add packages here in our studio that are available on the CRAN from here. Okay, or you can use the install.packages function that we've mentioned earlier. Okay, so now we're going to use the fit dist, which is to fit distributions, and now again we can actually test for a variety of distributions using the mass fit dist function. You can actually search for more information in the help page, and you can have an idea of a variety of distributions that you can actually use to test using this function. Okay, let's go back to plots. Okay, so that's the first step. So here it estimates both the shape and the rate. And so now we can actually rerun this line, but this time actually save them as the parameters, because this is the estimated shape and rate. So let's just save it in an object here that we call gamma.par. And now we can actually look at this structure and see the estimates that we've just seen earlier, the standard deviation, and other interesting parameters. And so we're going to actually be interested in the estimates, because that's what we need to use for our theoretical probabilities. So we're fitting the distribution, And we're using these. So now we're going to use those parameters to generate a plot similar to our QQ plot that we've shown earlier. So by looking at the structure, we can see how to get the shape and rate estimates as follows. So here, we can just write it like this. So we get shape, and let's save this in an object we call S. And then let's do the same for the rate. And then now let's do again the theoretical probabilities, sort of like how we had our theoretical probabilities earlier. Now we can directly add. So if we look at this, you will see here is it's a sequence essentially from 1 to length probe divided by length probe plus 1. So yes, it's a sequence of 1 to the length of probe A, which is essentially, if we look at this, length of probe A is 42. So 1 to 42 divided by length of probe A plus 1, which is 43. But writing it out like this means that we can easily reuse this function with other probes. We just have to store those values in the probe A object. Okay, so now let's get our theoretical quantiles, which is what we need now, using our theoretical probabilities and the shape and rate that we got from the estimate fit this function. And now we can generate a similar plot where we have to look at the fit. And so now you see we have a gamma QQ plot. And the next thing we're going to do is create, again, that line between that we had done earlier with the normal distribution. So now we're going to also use QQ line to actually put our theoretical line that for the theoretical gamma distribution on our fitted data. And so, to do this, we need to have a distribution. And if you read the QQ line help page, and if you actually look at what the QQ line function takes for the distribution is, so if we look up the help page, you'll see that the QQ line takes your values, and in this case we just sorted them for probe A, and then we have the distribution QF here, which is the function that we're defining here, which is Q gamma, so the function of P, which is the probability, so Q gamma probability with shape of S and a rate of R, and we store it in this, so QF object, which is essentially a function. And earlier, when we used QQ line, well, we didn't sort the values, but we could have, I suppose. But anyways, we had our probe A values, and then we had distribution equals Q norm. And if we look at Q norm is actually a function. And when we look at the help page for QQ line, we realize that the distribution parameter actually takes a quantile function for reference for the theoretical distribution. And so that's what we're doing here. By creating this function, we are essentially creating something equivalent to the QNorm function, which is used for the normal distribution. Something like this, where now we have the QQ line added, so the theoretical line added. So again, the central values look pretty good, but, you know, the tails are actually very different. Now we can actually run statistical tests to actually check whether or not our data points actually do fit the theoretical distributions that we tested. Our data points actually fit a gamma distribution. In this case, we'll just use a shape equals to 3 here and a rate equals to 2. Okay? So let's run the KS test. And so before we actually run the KS test, we have to remember with statistical tests, we're always testing our null hypothesis. If we cannot accept the null hypothesis, or if we have to reject it, in other words, then what is the alternative hypothesis that we'll be accepting in that case. Okay? So to do that, we're essentially looking at the p-value to see whether or not it is greater than our alpha, which is, in this case, most of the time it's a p-value of 0.05 or alpha of 0.05. Okay? So here, the KS test, the null hypothesis is that the data points actually follow, in this case, a gamma distribution. So the KS test, if we accept the null hypothesis, means that our data points follow the null. So now if we run the KS test, we'll be able to test whether or not our data points fit the gamma distribution by deciding whether or not we can accept the null hypothesis, which would mean that it does, or if we have to accept the alternative, or if we have to accept the alternative hypothesis, which is that it does not follow this distribution. And so, since our p-value is less than alpha of, in this case, it's 0.05 that we're interested in, and you will remember this is a p-value less, or significance of 0.05, right? Since it's less than, then we cannot accept the null hypothesis, and so we have to reject the null hypothesis in favor of the alternative hypothesis, which is that it does not follow the gamma distribution, at least with a shape of 3 and a rate of 2. Now, let's run it a different test to actually test whether or not our data actually fit a normal distribution. And so in this case, and if you forget, it's okay. You can always go back and do a quick search on the internet, or you can actually review your textbooks to remember what's the null hypothesis versus what the alternative hypothesis is. And so here we'll need the NOR test package, so we can actually run the ad.test function, and then we can actually run the test on our data points. And as you can see, our p-value in this case is greater than alpha of 0.05, right? So it's greater than 0.05, and so we cannot reject the null hypothesis. And so this means that our data points actually do follow a normal distribution and not a gamma distribution if we were to compare these two tests. So this is because our p-value is greater than 0.05, so I cannot stress that we cannot reject the null hypothesis. And since the null hypothesis for the ad.test is that your data points fit a normal distribution, well then it suggests that indeed our data points follow or fit a normal distribution. So in conclusion, I've just shown you how to fit your data points to the normal distribution with the QQ-norm function. I also showed you how to test other distributions with the fitDist function available in the mass package. I then showed you how to add theoretical lines using the QQ-line function. And then we concluded by testing our fit using two different tests, the KS test, or the Kolmogorov-Smirnov test, the Anderson-Darling test, using the ad.test function available in the NOR test package. Now in the next video, we'll be looking at other statistical tests to fit distributions. So thank you very much, and see you in the next video.
Hi, and welcome to Fundamentals of R Programming. In today's video, we'll be looking at other statistical tests to fit distributions. In this video, we are going to take a look at the fitDist function, which is used to fit a variety of distributions and is available in the propagate package. And then we'll use the AIC criterion or value to choose the best distribution. So let's just jump in. The first thing we're going to do is load the propagate package. So if you haven't installed the propagate package, we can do so as follows. Which will allow you to install the propagate package. And once it's there, we can load it by entering library propagate. So it's loaded. So the first thing we're going to use essentially is the fitDist function, and if you'd like to learn more about this function, you can search for it on the help page. So here, fitting distributions to observations / Monte Carlo simulations. You can read more about this function in itself, but it's very useful. For example, when you have a set of data points and you'd like to know which distributions or how well does these data points fit a particular known distribution. So for that, let's just set the seed, which will allow us to get reproducible simulated normal values. So here we're using the rnorm function, and like we mentioned in the earlier video, rnorm essentially allows you to simulate a number of values, where here n is equal to 10,000, and the next value here is of a mean of 5. So if you go mean, you can see the mean is 5, and if you want to know what standard deviation, it's 0.99. So SD is a function that allows you to see the standard deviation. So that looks good, and you can even look at the first 6 values. So head observations here, and you can see here we go. Next, we're going to use the fitDist function on these observations, and then look at the AIC values for these functions. So here you'll see it's now fitting a variety of distributions. So in your R console, you'll see normal, skewed normal, generalized, log normal, scaled / shifted t distribution, etc. And then if you look at the structure of this results object, it's actually quite large, so you can actually go into this in more detail. But to summarize, we could just look at the names. But essentially there is, if you go through this, an AIC that you can pull up in this results object as follows. So you see now, by doing so, I can get the AIC value for each of the distributions tested. So generally a very negative AIC value would suggest that our data points actually follow a skewed normal or Johnson SU or generalized normal distribution versus or compared to an arc sign distribution where the AIC value is very low. So highly unlikely, doesn't fit that distribution as well. So you can also use the fitDist function to fit results obtained from the propagate function. So if you want to learn more on the propagate function, we can do so as follows. So propagation of uncertainty using higher order Taylor expansion and Monte Carlo simulation. So this is a bit advanced, but I figure I would just show you real quickly how it would work, or how we would use the fitDist function with this. So let's say we have x and y values here, and we combine them to form a data frame, and then from this you run the propagate function, and here we're just doing a simple stat. So if you look at type here, stat, it means either stat if means and standard deviations are supplied, and then raw if replicates are given, or sim in case of simulated data. So you can actually change the type, you can ask it to do the simulation, so do.sim equals true, and verbose equals true allows us to see everything. So we will run this here, and you'll see express is not found. So, oh, I forgot to include the expression. So here we add it. So let's start over, and you can see it's looking at this, and then after you fitted the distribution, you can take a look at the AIC values, and here you go. So these are just quick ways that you can actually, or at least the fitDist function, if we go back, part of the propagate package is actually quite useful if you just have some sample points and you want to see how well they fit these 20 or 21 or so distributions. So in summary, what I showed you was how to use the fitDist function with either simulated data, but this could be any data points that you have that are from your population or sampled from a population. It could also be data generated from, like, say, a function, or like 3x plus 1 or any other expression. And I also showed you quickly how you can integrate that data with the propagate function and then use the fitDist function to see how well it fits the provided known distributions. And since this is our last video for this section, I'm just going to summarize what you should have learned from this section. First, we looked at descriptive statistics such as mean, standard deviation, range, etc. Then we went through really briefly an overview of probability distributions and how we use probability distributions in R. So how to add suffixes like R for random simulations from that probability distribution, etc. Then we learned how to fit probability distributions. And then in today's video, we use the fitDist function from the propagate package to test a variety of distributions in a single go. For our next section, we'll be looking at hypothesis testing and statistical models. Thanks for watching, and see you in the next video.
Hi, and welcome to Fundamentals of R Programming. This section will be covering hypothesis testing and statistical models. In this section, we are going to take a look at model formulas, 1 and 2 sample tests, linear regression, analysis of variance or ANOVA, and linear models for gene expression data. More specifically, in today's video, we'll be taking a look at model formulas. So in this video, we are going to take a look at model formulas and how they're used in R, and more specifically how the tilde, or this symbol here, is used, essentially to be able to look at response variables as response variables in response to explanatory variables. Module formulas. So essentially the tilde symbol that I've shown you earlier signifies that the response variable is modeled as a function of the explanatory variable. So usually the right side of the module formula specifies the number of explanatory variables and their attributes. These can be continuous or categorical. The next would be to specify any interactions that may exist between the explanatory variables, and if required, any nonlinear terms, which we'll see what the symbol is shortly, and in some special cases, offset of error terms. We will not be going into too many details for module formulas because for the most part, at least in bioinformatics, you're mostly dealing with a set number of explanatory variables, or it's very rare that we try to offset any error terms in our analysis. But nonetheless, this is something you can do in R using module formulas. Okay, so here's an extremely simple example of R code that can be applied and where we use the tilde symbol if we'd like. So in this case, just you can do this in your own R Studio or R console. Essentially, you just need to create a vector. In this case, we're creating a vector x that contains values 1 through 4. And then the next thing is we're going to define the type. So in this case, we'll be using the repeat function because it facilitates this process, and repeat a and b each twice. So when we do that, we now have a vector and a factor. And so what we could do with the tilde function, so essentially remember our response variables in this case will be 1 to 4, the values 1 to 4, and you can imagine this is gene expression data, And then the explanatory variable in this time would be the type. And so we have type A and type B. For example, group A or group B, or condition A versus or condition B, or even like knockout versus wild type, etc., etc. So writing it like this, we can instinctively see that by using the tilde variable, it separated my values in X and then grouped them, and then my box plot is showing us the relationship between these two. So between the type and the values in X. But module formulas can go a lot further than just, like using the tilde. There are many symbols you can use for statistical modeling. Again, some of them we'll be using, but for the most part, it's a bit advanced, so I definitely suggest you reading up more on model formulas, either in our book, Mastering Scientific Computing with R, or, there are good, useful tools out there that would be able to explain this in more detail. But I think it's good to have an idea of how these symbols are used in R in the event that you start to use more complex models when looking at your data. So symbols used for statistical modeling in R, we have the plus sign, which when used in the context of a model means inclusion of an explanatory variable and not addition. The subtraction sign or minus sign is used to delete explanatory variable in your model and not just as a subtraction. Star is used not for multiplication, but to include explanatory variables and their interactions. And then we have the division sign, which is not used for divisions, but rather nesting of explanatory variables. And then this vertical line here is used almost like you would in Boolean statements, y as a function of x given z. Then we have colons that can also symbolize simple interactions. So in this example, it indicates a two-way interaction between A and B. And then this actually here is not a vertical line, it's a capital I. And what it is a function that allows you to override the interpretation of a model symbol so that it could be used as an arithmetic operator. So all this will become a bit more clear in some examples. So here's a good example where we use the I function. So if we just did y tilde 1 over x, and we use this as a model, it would be interpreted as fit x nested within the intercept. Because I forgot to mention, but 1 is essentially the intercept of your model. Whereas if we had y tilde I parentheses 1 over x, then it will fit 1 over x as an explanatory variable. So you see how the I function changes the interpretation of our model formula. Now for categorical examples or variables, let's consider A and B. So here's a simple example. So y tilde A divided sign B would mean fit A and B within A. That's what it means essentially, A nested in B. So if we go back, see, the division sign was nesting. But this formula could also be written in several ways, because you can use a combination of symbols because they kind of relate to one another. So in this case, for example, a simpler way, I would say, of writing this formula would be y tilde A, so essentially A plus AB, the interaction that exists between A and B. Otherwise, the third notation you can use is the y tilde A plus B, but in this case use the match Boolean operator, so which is percentage in percentage A. But I think the easiest of the three, which is easy to remember since colons are always used for interactions, would be y tilde A plus AB interactions. Okay, now on to interactions. So to fit all the main effects and interactions, we often use either, like I mentioned earlier, the colon,
or we can even use the multiplication sign, which is in the case of our building our models. Or in this case, another way you could do it would be, for example, if you wanted to assess A, B, and C, but also all the interactions between these three explanatory variables, well, then you could just put in brackets, in parentheses, A plus B plus C, and even if it's written to the power of 3, it will be interpreted as all possible interactions between A plus all main effects and interactions of A, B, and C. Otherwise, we could have done A star B star C, or you could have written it all out. So when we're looking at the main effects, we're looking at the main effects of A, B, C. So we're looking at the interactions of A, B, C separately. So A plus B plus C. And we are also looking at the interactions. So plus AB interactions, plus AC interactions, plus BC interactions, and finally plus interactions that exist between A, B, and C. So you can see how this quickly becomes complicated. So really it's just so that you're familiar with the notation, so that when you read other code, or eventually when you get to more complex explanatory variables, or at least want to test more complex relationships between your explanatory variables and the response variables, you're aware of some of these tools in R. Finally, we can look at other interactions, such as to fit the main effects and the two-way interactions, excluding the three-way interactions. For example, one way to do this would be, so again, in parentheses, A plus B plus C, but this time only to the power of 2, so it will test all main effects and two-way interactions, but it will not test the three-way interaction. Another way of writing that would be to do A star B star C, which is essentially testing all main effects and interactions, and then subtract the three-way interaction, which is A colon B colon C. So that was it for module formulas. Again, it was just mostly the theory behind it and to give you some examples of how it is used. But then now in the next videos, we'll actually be using very simple module formulas, and we'll learn more about how to use module formulas in the context of statistical tests in the upcoming videos. This was mostly an introduction to introduce you to module formulas in R. And so in the next video, we'll be looking at 1 and 2 sample tests. So essentially looking at the difference between the mean of your sample distribution or your samples to either a set mean. So example, this would be a 1 sample test, or looking at comparing the mean of 2 different sample populations, or the mean of 2 different data sets. And so, thank you for watching, and see you in the next video. Hi, and welcome to Fundamentals of R Programming. In today's video, we'll be looking at 1 and 2 sample tests. More specifically, in this video, we're going to take a look at the Wilcoxon signed rank tests with the wilcox.test function, 1 and 2 sample t-tests with the t-test function, the f-test with the var.test function, and finally the Kruskal-Wallis test with the Kruskal.test function. Okay, if you haven't done so already, you can re-download the MLL dataset from the ArrayExpress site, or use the object that we created called mllxdataset.rdata from video 5.1 or video 5.2. And to do so, you just need to load Blooper. All you need to do is to change the working directory. All you need to do is change the working directory to the folder where this object is found, and then use the load function to load the data. So for our first example, let's look at some 1 sample tests, which are essentially used to compare your sample distribution to a known or theoretical, for example, mean. So in this case, we are going to collect, or at least load, the female heights that we collected by measuring So it said females heights, but it should be female heights. Okay, so when we do that, we see it's 151. However, say in a different study, it was published that the mean average height for females in the general population is 171 centimeters. Well, then we could use the Wilcoxon signed rank test to compare the mean of our sample distribution to a theoretical mean as follows. Okay, so as you can see, we have a significant p-value, which means that we reject the null hypothesis, which says that the two means are equal, and accept the alternative hypothesis, which is that the mean is not equal to 171. So this is very interesting. You can also, for example, modify other parameters in the Wilcox test. So you can look up what these are in the help function, or with the help function, or just directly here in the help tab. And as you can see, there are several parameters that you can play with depending on your question. Here's an example where we also would like the confidence intervals with a confidence level of 0.99. So if we enter this, then you'll see that it ran the test again, but this time it shows us the 99% confidence intervals, which is 120 to 175. And it also gives us our sample estimate, or pseudo-mean, which is 151, which we calculated earlier. The Wilcoxon signed rank test is actually quite useful if you cannot assume that your sample distribution follows a normal distribution or a Gaussian distribution, but say we could, then we could use the t-test. So this is a parametric test, and again we could do a one sample t-test with the t-test function in this case here, and then we again specify our theoretical mean, which is 171. And again we have a p-value below 0.05, which means that we can reject the null hypothesis and conclude that our sample mean is very different from our theoretical mean at, of course, a level or a significance value of p0.05. If we did the 1%, like we saw earlier with the when we ran the confidence intervals for 99%, it would fall between 120 and 175, which in that case would suggest that it would not be significantly different from the mean at a 0.01 confidence interval, like for a 0.01 significance level. Next, sometimes instead of comparing the sample means, you might be interested in comparing the variance between two sample distributions. And this is where re-downloading or loading the MLL dataset that we had used earlier is needed. So here we can use the var.test function, which essentially performs an f-test, to compare the variance of probe A and probe B. And as you can see, the variance is actually very different between probe A and probe B. So here with a very significant p-value, so this suggests that the variance between the two populations are not equal. Another thing you can do instead of running a variance or f-test and t-tests is the Kruskal-Wallis test. And this is a useful test because it allows you to compare two sample populations without assuming that they follow a Gaussian distribution. So for this example, if you just remember our probe A values, you can take a look here with head probe A, and then let's just artificially assign a drug response, either response or failed here. This should be failed. Response as follows. So we're just going to keep it simple and just have the first 21 samples respond and the last 21 samples fail. And then we can, here's where our model formulas come in handy. We could do Kruskal.test function with probe tilde drug response. So this will again model, or at least assign the probe values to a particular drug response and then look for the relationship between the two. As you can see, in this case, our p-value is actually above 0.05, which suggests that we cannot reject the null hypothesis. So what this means is that it suggests that the two sample populations are actually from identical or come from the same population. Finally, we can run some t-tests with these functions. Quite simply, here in this case, we could run a two sample t-test with just using the t-test function, and then this time using probe A and probe B as x and y. So if you want to learn more about the t-test function, you can look up the help page, or here you go. So here you see x, but you can also have an optional y, which in this case is probe B. And as you can see, it is very significant, so we reject the null hypothesis and accept in this case that the sample mean for both populations is different. So we don't need to actually plot a box plot to see what the values look like. They're actually here. So the sample mean estimates of x is 4.77 and the mean of y is 8.07. And so based on this parametric test, they are very different from one another, at least with a significance value of 0.05, but even 0.01 as you can see. And so as you can see, the p-value again is very significant, which suggests that the mean of the sample distributions are very different. So what if the values in probe A and probe B are paired? Or, you would like to do a paired non-parametric t-test. Well, in that case, you just have to use the paired argument as follows. And there you go. So you can see again it's significant, but this was just for learning purposes. And you could similarly use the paired argument here when running a t-test, in case you want to run a paired t-test. In conclusion, what I've shown you today is how to run some simple 1 and 2 sample tests. We learned the parametric t-test, and we learned the non-parametric Wilcoxon signed rank test. We also learned how to perform the f-test in R, and we concluded with the Kruskal-Wallace test function to run the Kruskal-Wallace test. And so now in the next video, we'll be looking at linear regression. Thanks for watching, and see you in the next video. Hi, and welcome to Fundamentals of R Programming. In today's video, we'll be looking at linear regression. In this video, we're going to take a look at how to perform linear regression with the LM function, and look specifically at an example where we create a standard curve from qPCR data to get the maximum likelihood estimates for the slope and intercept to be used for downstream analysis. So the first thing we're going to do is load our example qPCR data. So here we're just going to copy paste. Okay. And if you're curious as what the data looks like, we can use the structure function, and you see it's a data frame with GapTH as a factor, the RNA in nanograms, and then our 3 samples, A1, A2, A3. You can also, for example, look at the head as follows, and here you go. First thing we're going to create is an object that we'll be able to use with the LM function. And so, as we learned earlier, we can use the reshape package and the meld function to do just that. So let's do so, keeping the ID variables as GapDH and RNA and nanograms. And so now you see our object is again a data frame, but this time we have GapDH's levels, we have RNA in nanograms, and then we have our variables A1, A2, A3, and the CT value for each. So what this actually looks like, again, you could just use the head function. Take a look at what the melt function did, and essentially now it's much easier to work with because we no longer have our 3 columns for our sample values, and we actually have a single data frame with the CT values and as a variable the sample for each of the levels of RNA used in our standard curve. So for simplicity, so we don't have to use the with function. So normally we would use the with function with the name of the data frame, and then we could just call the column names. But to save time, we'll just use the attach function. And so what this does is that now, if you look at the list of objects you have available, we could just call or use these vector names to call the columns individually without having to worry about specifying the data frame name, or like data frame $, the name of the column, or even use the with function. So we can just directly call the columns. So here the first thing we're going to do is plot the CT values. And in order to see that our data actually does look linear, because you don't want to apply linear regression to data points that clearly don't look linear. And sometimes for this, so here it's a bit difficult to see, but if you just look at the raw RNA nanograms on the x-axis, and the CT values on the y-axis, you'll see that it doesn't follow a linear curve as is, which is to be expected. But if we log transform the RNA values, then we do start to see a much better linear pattern. And sometimes to be able to perform linear regression, we need to ensure that we transform the data so that it starts, at least it looks linear. So now we can just use the lm function, and again we're using that tilde symbol, which is used in module formulas, to say that here we want to look at the CT values as the response variable, and then the log of the RNA amount as the explanatory variable. And as you can see, it's just when you enter it, you get your call, so what was actually run, and then coefficients. So the intercept here being 23.87, and then your slope would be minus 2.23. That's very simple to do, and you can see that you get a nice curve here. So the next thing we can do, function, we can actually store this into an object that we call model. Okay, and from this we can just do summary model, and again we get a little bit more information. So we get the residuals, we get the coefficients, we get, here it's very significant, residual error, the degrees of freedom, the r-squared value, which you might be interested in. So in this case it's 0.89, and the adjusted r-squared value is 0.88, and finally the p-value. So what you can also do is plot the model, right? So let's hit enter. So it's going to come up in multiple frames. So here you see the residual versus fitted, the normal QQ plot, and you see it, look, we can see that information here. If we look the other way, we can look at residuals and fitted again, and normal QQ versus theoretical quantiles. I think it's a bit easier to see if we change the plotting parameters. So let's do that here. Okay, so that we only get one graph come up at a time. So here, hit enter. Yeah, so here we're first seeing the residuals versus fitted. So you can see here that we can maybe consider this as an outlier. We'll see. The normal QQ plot, so it looks quite nice. The scale location, so fitted values are shown versus the square root of the absolute standardized residuals, and residuals versus leverage. So these are actually good plots to look at to try and inspect for, among other things, outliers. But say we did have an outlier, in this case for teaching purposes, I'm just going to say I'm a bit hesitant. I'm looking at these graphs and 18 looks a bit weird, so I'm like, well, perhaps it's an outlier, so I want to remove it. I mean, from here it doesn't really look like an outlier, but nonetheless, like for teaching purposes, say we wanted to consider it an outlier, well then we can look at the point for 18. So it's RNA value 0.0116. The CT value is 37.2, so that's a really high CT value, so I'm not surprised. And then instead of like rerunning the LM function, etc., you could just use the update function. So how this works is it's telling you're creating a new model, so you're by updating the first model, and this time we're using the subset argument to remove the CT value, which is 37.2. So it's here essentially what it's saying is subset CT value not equal to 37.2. So keep all the rest. Okay. So here we go. And so now we can again do summary of the model 2. And we get useful information. It didn't really change very much, but it's important to see that we did do something, because here we have the call and it shows that it's been subset, so you can actually see the LM formula. Okay, just by quick curiosity, you can actually, look at the structure, so you can get this information. Shown more complex here, but it might be useful for you. And that's it. So essentially, by using the update function, we could easily just remove residuals, and this is how you can do it in R. And then you can look at your summary for statistics, and you can even, replot this model. So plot model 2. Like we did earlier. So here again we get the residual versus fitted, the QQ plot. In this case you can see it's actually a bit worse, actually. So I would probably not keep model 2. And look at the scale location and residual versus leverage. So you can see it was probably much better to keep the values, the CT values that are equal to 37.2, because it is giving some meaning. So our QQ plot actually looks a lot better in model 1 than it does in model 2. Okay, so that's pretty much how you run a linear regression. If you'd like to learn more about the function, you can just go here to the help page. So in summary, what we've learned today is how to perform linear regression with the LM function. We also learned how to use model formulas in the LM function and how to update our model by simply using the subset parameter, and then learn to plot the model so we can get potentially information that we could use to decide whether or not our model looks good. And so in the next video, we'll be looking at analysis of variance, or otherwise known as ANOVA. So thanks for watching, and see you in the next video. So hi, and welcome to Fundamentals of R Programming. In today's video, we'll be looking at analysis of variance, or otherwise known as ANOVA. More specifically, in this video, we're going to take a look at how to perform an ANOVA with the AOV function, how to summarize and update ANOVA models with the summary and update function, investigate the effects of different levels with the summary.lm function, compare two models with the ANOVA function, and finally, perform a one-way ANOVA with the Tukey ad hoc analysis to get an idea of the p-values for each pairwise comparison. So we can copy in the example. We'll attach the patient.fatigue data frame so that we just have to call the column names instead of using the with function or using the data frame name and then $sign to call the atomic vectors. And so if we take a look at the head of this data frame just to have an idea of what it looks like, here we go. So essentially, it just reports the fatigue level for each patient by drug response. So the first thing we're going to do is run an ANOVA. And so to do that, again, we're using a model formula where we have the drug A response by fatigue. so the fatigue level. And so here we ran an ANOVA, and you can see that it gives us the call that was run, the fatigue, the residuals, the degrees of freedom, etc. This isn't so meaningful as is for our purposes, so we are going to look instead at the summary of the ANOVA data. So essentially looking for the p-value. And so here it suggests that there is a significance between the drug response and the fatigue level based on the significant codes and also the p-value. And so what we could do is, instead of just running the ANOVA like that, we could store it in a model A object or an object that we call model A, so that we can actually plot the model like we did in the previous video. And so here you can see that it has again all that information, like the residual versus fitted, the normal QQ plot, the scale location, and residuals versus leverage. So this might be interesting or useful for you when assessing your model that you've created. And again, for the teaching perspectives, say here from the normal QQ plot, it seems that maybe a 3 and 20 are outliers. So let's update our model by removing patient number 20 and see what the effects is on the model. So instead of rewriting everything, we can just do update model A subset patients that do not equal 20. And so again, we can look at the summary of this model for more information. And so again, we see that it's again significant by p-value, but by removing patient 20, the p-value went way up. But since we're really only interested in a significant level of 0.05 or 0.01 or even 0.001, in both cases the model is significant. So technically we could keep patient 20 in our data set. Okay, so now what if we wanted to assess the individual effects of each of the levels? So in this case, our fatigue levels are high and low. We could use the summary.lm function as follows. And as you can see now, we have more information. You see the call, but importantly, you see that fatigue is actually broken down to low and medium, and the intercept is just your reference. So if we look at the levels in fatigue, you'll see that it's related. So we have high, low, and med. So what this means is that as a reference, the intercept is high. And here we're looking at, so here this would be, intercept is otherwise fatigue high. The second one is fatigue low, and then the last one is fatigue medium. So you'll realize that, so as you can see, each level of fatigue actually does relate back to, in a significant way, the drug response. Now we're again going to take advantage of some of the notations we learned from model formulas in video 6.1. And so what if we wanted to actually run an ANOVA for a drug A response, but this time by fatigue times patient.sex. So what that means is look at the association between fatigue and patient sex, and also the interaction. So the main effects and the interaction between fatigue and patient sex. So first, before even running that model, let's add the patient sex data that we have for each of those samples here. And then now let's run model C, which is looking at the main effects of fatigue and patient sex and also the interaction between the two. And as you can see, the relationship between fatigue and drug response is still there. However, there isn't significance when looking at patient sex and drug response, or the interaction between fatigue and patient sex and drug response. So in other words, the effects of gender and fatigue are not additive, and there is not a significant relationship between drug A dose and patient sex. So what if we compare both model A and model C? So the one where we actually included the interaction and main effects of fatigue and patient sex, compared to the basic, our first model, which was just drug response and fatigue. And as you can see here, we have model 1, model 2, and then we have some statistical information here. And what you'll see is that there isn't any, the p-value is not significant, which suggests that both models are technically valid. However, when choosing a model to represent your data, it's always better to use the simplest model. That's just a rule of thumb when describing your data. Ideally, you always want to use the most accurate but also the most simple model. I would suggest just publishing model A. Now, finally, another thing that is useful, especially when we look at performing one-way ANOVAs for gene expression data, but in this case, we'll just use our patient fatigue data. And this would be the simplified version, so not actually going through all those steps or even using the attach function to kind of be able to call your columns or your atomic vectors directly using the column name. Instead, you could simply write save our run the model with the patient fatigue data frame, run an ANOVA, a drug response by fatigue level, summarize these results as follows. And again, you see it gives us the response that we had earlier, which is that it's significant. And now, what if you wanted to know what the p-value is for each pairwise comparison? So in that case, it's best to perform an ad hoc test. In this case, we'd be running the Tukey test here. So Tukey multiple comparisons of means. And so here you actually have all pairwise comparisons. So low versus high, medium versus high, medium versus low, the difference between the two, and then the p-values. And as you can see, it's significant between low and high and medium and high, but not medium and low. And so this would kind of be the data you would need to kind of add the stars in your for the individual pairwise comparisons in your plot if you're used to working with Prism or Excel. And so you can actually save this information as follows into a data frame. So here I'm just calling it Tukey data frame, and you can look at the head here and you can see it has this information here, which we saw earlier, and then you can just save it as a table to work with in Excel or to share with the write.csv function. And so in summary, what I've shown you in this video is how to perform an ANOVA and how to perform model comparisons with the ANOVA function. I also showed you how you can summarize the information using the summary function and also the summary.lm function if you wanted to go by level or factor level. We also showed how we can use model formulas, for example, looking at the interactions to test if, for example, patients' two variables are additive. And finally, we concluded with like a simplified version of the analysis that you could do for just running a one-way ANOVA and the Tukey post hoc or ad hoc, or using the Tukey test to look at the multiple pairwise comparisons to look at the individual p-values. And so in the next video, we'll be looking at linear models for gene expression data. More specifically, we'll be looking at how to use the Lima package to analyze gene expression data. Hi, and welcome to Fundamentals of R Programming. In today's video, we'll be looking at linear models for gene expression data. More specifically, in this video, we're going to take a look at linear models for microarray data with the Lima R package. We'll look at how to construct model matrices, contrast matrices, and get differential gene expression using these linear models. So for this video, you'll need to make sure you download the appropriate ESET object that I've created. I've left you here the link where this can be downloaded. And then you just have to also make sure that you install and load the Lima package. Okay, so to do this, let's set our working directory. Let's load the ESET object. And then just to give you an idea, so this is from a GEO data set here, GSE 22093. You can read more about it. It's a breast cancer study. If you want, you can look at the phenotypic data. So here you see there's it's breast cancer. They've looked at P53 status, etc. And so for simplicity, we'll just copy the contents of the P data, the set object, into a new object called phenodata as follows, so that it's easy for us to retrieve the information that we're interested in, at least for the context of this study. Okay, looks good. So if you look at the column names for this object, you'll see that there are characteristics 1 through 10 in the treatment protocol, but we're interested in the characteristic 1.10, and if you're interested in that, you can just look at the head, again, of the phenodata matrix. And so we're just going to store the tumor grade as follows into a grade object. And so here I'm just showing you the first 6, which are grade 3 cancers. And then we're going to use this information to create groups. And I don't really like the notation if we look at the unique values for grade 1, 2, 3, and NA. So I'm actually going to simplify it so that we just have like grade 3 versus others. So we can simply make that comparison. So I'll create a function that will look at each value or each grade, and then if it's equal to 3, then it will give it a grade 3, otherwise it will call it other. Okay, so as you can see here, we've got the grade 3 status. So this is a simple character vector, and to be able to work with models or create models with Lima, we need to make sure that we work with factors. So here I'm just going to create a factor from our grade notation, and then have the levels be other and grade 3, because I put other first because I would like that to be my reference group, and then grade 3, the group I'm interested in. Okay, so if you take a look at group, you'll see that there's other in grade 3, and it looks like it should. We're now just going to save the expression matrix in M1, a new object, and the expression matrix can be retrieved with the express function, so exprs. And if you are curious, we can look at the dimensions. So it's 103 samples, and there's over 22,000 genes. So now we're going to define a model matrix, and this is the model that's going to be tested or used to fit your data in the later steps. We use the model.matrix function, and then we'll just save this into design. So this is just the design of our model matrix. If you're curious, you can look up the Lima user guide, or you can just look for model.matrix here, and then it just shows you that this function is used to create a design or a model matrix. And then here are some arguments you can tweak. But what we're interested in is just creating a model matrix using the groups we assigned up here as other or grade 3. So now let's look at a head, or the first 6 lines of our design matrix. So as you can see, you now have this design matrix with the intercept and group grade 3. And this is important. Why? Because it essentially means that other is the reference. And so this column here, group grade 3, means will show me whatever is grade 3 versus others. Okay? So it sounds a little confusing, but it's actually, once you get the hang of understanding that your reference sample is your level 1, or whatever stored in your first level, and then the next one is what your object, or sorry, your group that you're interested in. In our case, it's group that has grade 3 cancers. And then we're now, when we design this model matrix, by default, it will create an intercept, and it will create the grade 3 versus others. in this column, in the second column in this case. For those that it might not be as intuitive, so I'm going to show you another way how you can more easily grasp these concepts, which is using contrast matrix. But nonetheless, I think this is the quickest way to do a very simple analysis, which is grade 3 versus others. So what are the genes that distinguish those two groups? So now that we have our design matrix, we can fit our models with the element fit function and then eBayes. Get our differential expression. Then we can actually store the results in our res objects here. And then the top table is actually quite useful because it allows you to look at the top differentially expressed genes between grade 3 cancers and others. And so if you look at the dimensions, in this case we have the statistics for all 22,000 genes, and that is because we said n equals infinite, so all of them. But you could also just choose to show the first 10 genes, for example, here by changing this parameter, and now you have the first 10 genes, or in our case, the first 10 probes. And so you have the log fold change, the average expression, the t-value, p-value, and adjusted p-value. Otherwise, you can just, I like to store or get the statistics for all genes and then just print, for example, the first 10 genes with the head function. Okay, so you can actually save these results into a CSV file that you can open up in Excel or share with your collaborators, etc., using the write.csv function. Next, we'll learn another way you can actually do the analysis is to use contrast matrices. What's very great about using contrast matrices is that it allows you to look at multiple comparisons. So in this case, we're going to use our P53 status as the example. So these 3 lines of code is just to get my P53 status. I wanted to correct the n/a to nd because I don't want it to mix up with na. And then I'm creating a factor of the P53 status here that I'm storing in P53. And if you actually look at P53, you'll see it has mutant and D and wild type. So I didn't really change the order of the levels because when you use contrast matrices, it's easier because you get to pick your reference sample and your sample, like your reference sample and what you want to compare it to. Okay. So in this case, we again use the model.matrix function, but then we are using, and it's important to do tilde0 plus your factor. And this is because tilde0, by doing so, by adding tilde0, you'll no longer have that intercept column. So it will actually just label which sample is which. So this is a bit easier to see after we've created it. So here's our design. The levels are shown here. And now if you look at the call names of the design matrix, they're actually P53 mutant, P53 ND, and P53 wild type. So essentially, the level P53, the name of the factor, and the P53 status column. Next, we are going to fit our expression data using this design matrix. And once it is fitted, we can now make our contrast matrices. This is really much easier because you can actually pick the columns or predetermine which comparisons you want to make and not just use the default one that we had used earlier. So in this case, we're looking at P53 versus P53 wild type, so mutant versus wild type. So you'll notice that this is your sample versus reference. Sample versus reference. So P53ND, like minus sign P53 mutant means ND versus mutant. And again, ND versus wild type. And then you need to just specify that your levels are those of the design matrix. Once you've done that, you can do your contrast fit. So here you use the contrast.fit function, and then again you do your eBayes, use your eBayes function to get the differentially expressed genes. Okay, and so again we can just use the top table function, and by default I think it only prints the first 10 lines. Okay, so please just start from here. So after you've done your fitting, you've fitted with the contrast matrix, and then you've run eBayes to get your differential expression, you can look at the first pairwise comparison here, so p53 mutant versus wild type, by calling coefficient 1. As you can see, it prints the first 10 lines. By default, you can look at coefficient 2, which is ND versus mutant, and you can look at the third one, which is ND versus wild type, by doing coefficient 3. Okay, so say if you wanted to do 4, technically you should have an error because there isn't any. Okay, perfect. And a nice tool you can use that is or a function that you can use with Lima is the Venn diagram. Okay, so here, to get a Venn diagram of the results or pairwise comparisons, you can use the decide tests function and save it in results, and then get the Venn diagram by using the Venn diagram function. And so here it's kind of muddled, but you can see how many genes were differentially expressed between mutant and wild type, how much between ND and mutant, and ND and wild type. Okay, so this is really great tool, and this is just basics of using Lima or linear models or creating model matrices and contrast matrices. But we will learn more in the next course, which is bioinformatics with R. So we'll actually learn and go into more in depth how to get differentially expressed genes using other tools in addition to Lima. But so far, in summary, what I've shown you is how to create model formulas, how to perform 1 and 2 sample tests, so hypothesis testing, how to perform linear regression in R, how to run an ANOVA or analysis of variance, how to run linear models for gene expression data using the Lima package. So thank you very much for watching, and I hope to see you in the next course.